that going. Doesn't have the whole side yet. All right, so last time, what did we talk about last week? I guess it was the week before last week.
Area of triangles and...
Mostly areas, but yeah, areas of triangles, that's going to be a really important one. How do we calculate the area of a triangle?
It's half the base times the height.
1/2 the base times the height, perfect. And one of the other big ones that you'll use over and over again is the area of a parallelogram. The area of a parallelogram, remember that it's just base times height. And it doesn't matter how much you share that parallelogram, it's still base times height. So those are, we'll for sure use the triangle one today. I don't know if that parallelogram one will come up today, but so switching gears now. This next chapter is on circular circles and regular polygons. First off, what is a regular polygon?
One that's enclosed, right?
Is this a regular polygon?
Yes.
Yeah.
Now, so a regular polygon is a polygon where all of its sides and all of its angles are congruent. So a 3-sided regular polygon is an equilateral triangle. Not just triangle, equilateral triangle. All the angles are the same, and all the sides are the same. A 4-sided regular figure
Is a square.
is a perfect square, yeah. All right angles, all side lengths the same. A 5-sided regular polygon, perfect pentagon, and hexagon, and heptagon, etc. So that's what it means to be regular. So we're going to be talking about regular polygons and circles. That's what the chapter's heading is. Make sense with that?
Yeah.
Okay. Now, something we're going to be doing a lot is inscribing shapes in circles and inscribing circles in shapes. So, our first theorem of the day is going to be there's exactly one circle circumscribing a given triangle. So what does it mean for a circle to circumscribe a triangle?
It needs to be on the exterior of it.
So you start out with any random triangle you want. I'm just going to draw some random triangle. Not trying to do it in any particular way. I kind of don't want to make it too nice. Let me draw one a little bit uglier. Although, that will also put my drawing skills to test when I come to circle. But so we've got some triangle here, ABC. A circle that circumscribes the shape is a circle that goes through all of its vertices. Not every shape can be circumscribed by a circle. Let me give you one really quick. Try and draw a circle that goes through all those vertices. It has to go through this point, this point, this point. If it's going to go through those 3 points, the circle already has to look something like this. But it also had to go through that point, that point, that point. Can't do it. So not every shape can be circumscribed. Our first theorem is to prove that every triangle is circumscribed by one and only one circle. So first, I need to prove that there is a circle in existence that goes through all 3 of those vertice points, and then I need to prove that it's the only circle that goes through all 3 of those vertices. That make sense?
Yeah.
So this is theorem 7-1.
11-1.
11-1, thank you. Theorem 11-1, and every triangle is, I assume that they're circumscribed, and what's the other word? Inscribed. We say the triangle is inscribed in the circle, or the circle circumscribes the triangle. So, I'm not sure which word he uses.
Circumscribing.
They're exactly circumscribing. There is exactly one circle circumscribing a given triangle.
Every triangle is exactly one circle circumscribed.
Oh, every triangle.
Yeah.
Every triangle is exactly one circle.
We got everyone. Every triangle is circumscribed by Sorry. Circumscribed by exactly one circle. Something logically equivalent to that. Well, if you guys have your book out, I'll just have you start reading those to me so that
Okay.
I don't do something weird. Okay, so how does this proof work? So I gotta find the circle that circumscribes this triangle. Now, there's a useful theorem that we did a while ago that I want to remind you of that I'm going to use here. So, flashback earlier in the course, we proved that if I had a segment AB here,
There are points on the other side. Is that what I'm saying?
so that's one thing, but now I want you to find a point equal distance from A and B.
Perfect center.
So there's this point, and here's one of them. Is that the only point equal distance from A and B?
Yes.
No, that's the only point equal distance from A and B on the segment. Are there other points not on the segment?
Yes.
Where are they?
No.
Perfectly
Equal
up,
distance
perfectly
from
up.
A and B.
So let's pick a point right here.
Oh, yeah, okay.
Is that equidistance from A and B, roughly, based on my
Yes.
picture?
Yes.
What about right here?
Yes.
So what are all the points equidistant from A and B?
They are perpendicular to this bisector. They are perpendicular.
They're all the points on the perpendicular bisector. That is exactly right. All those points are the points whose distance from A and B is the same. Okay, so coming back to this, I am trying to find the circle that contains the point A, B, and C.
Yes.
What's the definition of a circle?
Isn't it an undefined?
No, a circle has a definition. If I were to give you a point that we call the center and some radius r, we'll say that the length of the radius is equal to 3, and that's our center. What's the circle? It's all the points whose distance from the center is exactly 3. So, if I am looking for a circle containing the points A, B, and C, what do I need to do? I need to find some point, O, such that its distance from C is the same as its distance from A is the same as its distance from B. Right?
I don't understand what you're saying.
So, if A, B, and C are on, if there is a circle that contains those 3 points,
Right.
then that means that there has to be some center I can find and some radius I can choose such that these 3 points are the same distance from that point. Right?
Right.
That's the trick to this problem. I need to find that point. I need to find some point such that if its distance from C is 5, its distance from A is also 5, and its distance from B is also 5. They all have to be the same distance from that point. Otherwise, they won't lie on the circle centered at that point. So that's a defining feature of a point being on a circle. Its distance from here is exactly the radius.
Yeah, okay.
Okay.
I see what you're saying.
So now, what are all the points whose distance from A and C is the same?
A and C, the midpoint.
That point has its distance from A and C the same. Is that the only
Everything
point?
perpendicular to it.
Its entire perpendicular bisector. Perfect. So all these points have their distance from A and C the exact same.
Right.
Yeah.
Now, if I draw the perpendicular bisector for this one, it has all its points from A and B the exact same.
Right.
So anywhere on here, the distance to A and B is the same. Anywhere on here, the distance to A and C is the same. So this point right here, what do I know about that point right there?
It's the center of the
It's the
circle
mid-
containing B and C.
A circle.
Well, that's what we're going to get to. I know that the distance to B is the same as the distance to A is the same as the distance to C.
Right.
Right?
Yeah.
Since it's on this perpendicular bisector, I know that this distance and this distance
Are the same.
are equal. And since it's on this perpendicular bisector, I know this distance and this distance are equal. And therefore, if I were to pick this point and use this as my radius, so set up my compass here and draw a circle, then that circle would perfectly contain all 3 of those points. You see it?
Yes. Yeah.
It's ready for that.
Yeah.
Okay.
Yeah, I see.
Now, how do I know that there isn't secretly some other point where I could have also drawn a circle? So I know that there's at least one circle that I can draw that goes through the points A, B, and C. So far we proved that. How do I know that there's only one circle? Could there have been some other point I used?
No.
How do you know?
Wait.
They only, the two
Because
lines
that's
only
where they only
cross one
intersect.
time.
Perfect.
That's the
Wherever the center is, it has to have its distance from here and here the same, and it has to have its distance from here and here the same. Which means it has to be on this thing's perpendicular bisector and this thing's perpendicular bisector. And those two perpendicular bisectors cross at one and only one point.
Right.
So I know that there's a circle, and I know that there's only one circle. That makes sense?
Yeah.
Yeah.
Okay, that's the first proof. Good?
Yeah.
Okay. Let's see, number 2.
Are we just skipping 10?
We did chapter 10. That was area.
Oh, was it? I thought.
There's exactly one circle that circumscribes a regular polygon.
Oh yeah, got you to help me out here. Okay.
So it's the same thing, but regular polygons. It's a triangle.
Yeah, there's exactly one.
So theorem 11.2.
Yeah.
Just read me the verbiage verbatim.
There's
There's
exactly
exactly one circle that circumscribes a regular polygon.
There's exactly
one circle.
one circle. What? Circumscribing?
That circumscribes
Circumscribes.
a regular polygon.
Scribes a regular polygon. Okay. So what is a regular polygon?
A regular polygon is where all the sides are equal.
They're all equal and all the angles are equal.
And all the angles are equal.
Congruent.
Congruent. Okay. So, gonna start out with some regular polygon. I'm gonna draw a hexagon, but it doesn't matter which regular polygon we draw.
Right.
The argument's the same.
Which one?
If it were a triangle, we've already proven that.
Which triangle is a regular polygon? Who really prove it?
So, going to start with,
A triangle regular polygon.
I'm going to draw a hexagon for the sake of an arbitrary polygon, but nothing special about the hexagon here.
Hexagon has 6 sides.
Yeah. Not great. Good enough. So there's our starting polygon. Maybe try and use red for the circle that's going to circumscribe it. Well, here's the argument. Maybe label some of these points. And maybe let's actually write this one out. Don't want to make so that you guys never see proofs again. Make sure you still want to feel comfortable writing these out if you had to. So let's actually write this one out completely.
We write it down in homework still, but yeah, I see what you're saying.
So 1, let A, B, C, D, dot, dot, dot be the vertices, is that right? That looks wrong. Vertices of an n-sided regular polygon.
Inside means the length of those are n.
No, it means there's a total of n sides. I don't know how many. So it could be 6. I drew 6 here.
Oh.
Could be 6, could be 7, could be a 10-sided polygon. And I don't know what all its vertices are. I only need to name the first 4 for the sake of my proof, but it's going to have some number. Okay. 2. Let O be the center of the circle circumscribing triangle ABC. So I already know that there is a circle that circumscribes ABC.
Not triangle, it's part of polygon.
Why wouldn't you just
ABC is a triangle. Look.
I see what you're saying. So you're gonna do that, you're not gonna do.
Why don't
This is still a triangle right here, right? Go ahead.
if a polygon has all the same sides and angles, why can't you connect a line through C and F, E and B, and D and A, and say that midpoint you find, because they'd all be equal distance from that midpoint, right? So why can't you just draw a circle from that midpoint? Shouldn't it touch all vertices?
So you've got an idea about how to go about arguing this. You're saying, look, take the perpendicular bisector for each side,
Yeah.
and then argue that all of those points, you'd have to argue that all the triangles you create are all congruent, and therefore, that's a circle that contains all those points. And we're gonna take your same idea, roughly, we're gonna take that idea. I'm just getting my starting circle from this proof, and then I'm gonna basically do exactly what you're saying.
I think what he's talking about is
I was saying
connecting the
connect
dots
C
between
and F,
A and D.
D and A, E and B.
Oh, maybe I did misunderstand you. You're saying,
Yeah,
You're
he's
saying
not saying use
connect
perpendicular
C and F.
bisector. Yeah,
Yeah.
he's not using saying
Yeah.
use perpendicular bisector of each.
okay,
I can't see
E
that
and
at
B.
all. Look,
And D and A.
A and E,
E and B.
E and B.
E and B.
And then D and
Okay, so connect all those.
Saying that midpoint is the center of your circle.
How do you know that all those intersect at the same point? Your intuition tells you that you do, that they
A.
do.
Because the same sides and angles wouldn't.
So I know that this angle is the same as this angle, but how do I know that this piece is the same as that piece?
How do you know that? You can't do that.
Right, maybe the angle sum here is 120 degrees, but maybe this one was split into 80 and 40 and over here was 60 and 60.
No.
You would have to argue that those are all split the exact same way.
C and B, C and B and E and F would be parallel, so they couldn't, right? It couldn't
You're saying
be
these two
A-
sides are parallel. How do you know?
Same angle and same length. Same angle.
Right, there's all these nice properties you are expecting this thing to have. In this chapter, we're deriving a bunch of those properties that you're already wanting to use.
So you can't use this.
You could go about arguing this way,
If you could.
But what if it was
but you're basically gonna have to somehow come up with a way of arguing that all these triangles are congruent to each other. Which is gonna be really hard to do. I don't see a way to do it off the top of my head without using their altitudes. Which is the same concept we use over here.
But you're trying to do what?
So, well,
those triangles are similar?
you might have I think if you kept fighting with this, you'd be able to prove it this way. I think you have a good idea for how you could go about proving it. But I think you'd end up coming back to the same logic that we're ultimately used here. I think you'd come back to drawing those altitude lines and not just the lines from the vertices. That's what I think would end up happening. But yes.
I thought
I
by
think
the
it-
definition of a polygon, you could prove it like that.
Nope. All we know is that all their side lengths are congruent and all their angles are congruent. That doesn't tell us about any of the diagonals in them. Those are things that need to be proved separately. It turns out they have the nice properties you expect them to have, but that's something that has to be proved separately. All right, so we start with, notice ABC here, we can create a triangle with ABC, right?
On the other one,
ABC,
on the
yes.
other option, you still don't know that.
A, B, and C are a triangle. There's 3 points. 3 points to find a triangle.
Right.
So I got a triangle. I know from this theorem over here, there must be a circle that goes through these 3 points.
Right.
So, I'm going to draw that circle. See if you can see this better than you can see the red. Sorry, missed one. Something like that. You got the idea. So, there's our circle. Centered at O. So far, all I know about that circle is it for sure contains A, it for sure contains B, and it for sure contains C.
Right.
My argument from here on out is going to be, and it also contains D. You with me?
Yeah.
And then, since I know it contains B, C, and D, I can use my same argument to argue, therefore it also contains E. And then since it contains C, D, and E, I can use my same argument to say, therefore it contains F, and G, and H, and any arbitrary number of points it had.
Because you can make triangles with all of those.
Right. So, my proof is going to be one that you can just reset and swap out your letters. And that way we prove it for any n number of sides. The way we'd actually do this is called a proof by induction, but it's kind of a messy proof technique to show you. So, we're using the logic of proof by induction without actually doing a proof by induction. Sorry, I'm going to have to indent this. I wasn't paying attention to my picture. Alright, so let O be the center of the circle circumscribing triangle ABC. So I know it contains that. Now, I'm trying to argue that D is also on the circle. How do I argue D is also on the circle? I need to prove that the distance from O to D is the same as the distance from O to C.
C to O, right.
So I know that A, B, and C are all on the circle.
Right. You know, A.
So I know that whatever this distance is the same as this distance, is the same as this distance. We're trying to argue is the same as this distance. That's where we're trying to get. You with me?
Yeah.
Yeah.
Because if this distance is the same as this distance, then D's on the circle. That's what it means to be on the circle.
Right.
You're exactly the radius's distance away from the center.
Right.
That's what the circle is.
Yeah.
Okay. So we're trying to prove D's on the circle, or in other words, we're trying to prove that this distance is the exact same as the radius.
Yeah.
Okay. Now I know that this is a regular polygon, which means I know that this side length is congruent to this side length, is congruent to this side length, is congruent to this, is congruent to this, is congruent to this, right?
Did you skip a step in your proof?
No.
Wouldn't you say let ABC be a triangle and
You did.
Let O be the center of the circle circumscribing triangle ABC.
okay.
Okay. So now, the next thing we're going to notice is that triangle OAB is congruent to triangle OBC by,
You have to prove that?
look at the picture. We can just observe it. I don't think we need to
By
prove it
side,
separately.
side.
By side, side, side. Triangle OAB, let's see, we did radius, base, radius, is congruent to triangle
BC.
OBC by side, side, side. Okay, so I now know that these two triangles are congruent, right?
Right.
Which tells me that this angle
It's congruent to that angle.
is congruent to that angle.
And so on and so on. And so
Hold on. We gotta be careful here. Also, observe that triangle OAB and triangle OBC are isosceles triangles. So in other words, their base angles are congruent. Their base angles are congruent. So what am I saying there? So first off, we're looking at two things. Let's stop. Forget that this is congruent to this for a second. Let's put that on hold. First, notice that this is an isosceles triangle, right?
Right.
This side and this side are the same length.
Right.
When you have an isosceles triangle,
You know, the base angles are the same.
I know that the base angles are also congruent. If these sides are congruent, these base angles are congruent, right?
Yeah.
So this is an isosceles triangle, so I know that this angle is congruent to this angle. Furthermore, I know that this triangle is congruent to this triangle. So now this angle is congruent to that angle, and this angle is congruent to that angle.
I have a question.
Go ahead.
If B and A are the same distance from
Oh.
O, are B and A the same distance from each other as from O?
No.
No, not necessarily.
Let me give you an example. O could have been right here. These could have been A. This could have been B. I happen to choose a hexagon, and when you draw all the triangles inscribed in a hexagon, then you get 6 equilateral triangles. So in my picture, that happened to be the case. But I could have used like a 1,000-sided regular polygon going around here, and then the triangles would have been really skinny.
Okay, yeah.
So A and B are the same distance from O, not necessarily the same distance from each other. It's probably a good argument not to use a hexagon. Probably should have done an octagon.
Okay.
Okay.
Just a bigger hexagon.
Well, you still have the same picture with your triangles.
Would you?
Yeah. Doesn't matter how big you make the hexagon, you can divide it into 6 equilateral triangles. All right. So anyways, I know that that angle is the same as that angle, is the same as that angle, is the same as that angle. Furthermore, I know that this whole angle right here is the same as this whole angle right here.
Right.
Because it's a regular polygon.
Right.
So if this whole angle is the same as this whole angle, and that piece is the same as that piece, then this piece has to be the same as that piece.
Right.
Or in other words, this angle is also congruent to those.
And then, right. Same thing for the side and so on and so
So
on.
that's my next line here, 5.
Side, angle, side.
Since angle, start with the right angles, DCB is congruent to angle CBA. Since that's congruent to that, since angle OCB that should be an and there. Since that and angle OCB is congruent to angle OBA, then that gives me that angle, we'll start with O, OCD, angle OCD is congruent to angle OBC. The high level way that we say that is equals subtracted from equals are equals.
Right.
So erasing what we didn't know for a second, here's what we knew. Since red is congruent to red, and that little blue is congruent to that little blue, then that little blue has to be congruent to that little blue.
Right.
Okay, so then we get, looking at this triangle, what do we know? Follow the triangle, what do we see, what do we know?
For side angle side, both the triangles must be congruent.
By side angle side, this is congruent to this.
Right.
So then, triangle, make sure we do it right. We'll do side angle side, so triangle OCD is congruent to triangle triangle OBC, which gives me that their corresponding sides are congruent. So, which gives me that OD is congruent to OC. So, OD is congruent to OC. 7. Therefore, D lies on the circle. Okay. And now we can repeat the proof starting with the points B, C, D to prove that E's on the circle. Right?
Right.
And so we can extend that indefinitely. Any questions on that proof?
You just get triangles and show those two are congruent to each other and all the way around.
Right, so we could repeat the exact same proof, just relabel everything. So,
Yeah, I have a question. Can you
7 we could say now relabel B, C, D as A, B, C, and repeat or whatever. Something like that. I don't know why I erased my last line. Oops, that was still worth using. But you can just relabel things and restart to prove that this is on it with the exact same logic. Relabel everything, call that A, B, C, D, E, F, and now you can once again prove D is also on the circle. Prove D is also on the circle, keep going around, is what I'm going to say. That make sense? You guys alive?
That makes sense.
Yeah.
All right. So no questions. Were you asking something?
On your second proof, on your second part of your, on your, what it's called?
A picture?
No, the second one, the second,
Number 2?
number 2. Do you have to say that, do you have to describe what circumscribing ABC is? Like, do you have to say, there's a line from, this, like, do you have, do you have to
Just say
describe
there's
your
a-
point, same from A, B, and C?
No.
Like,
When I say that these 3 points are circumscribed in a circle, centered at O, what that means by definition is the distance from A to O is equal to the distance from B to O is equal to the distance from C to O.
okay, so you don't have to describe.
No, you don't need to describe what circumscribing is. It's a defined term. We might skip the definition. What does it mean to circumscribe a shape? It means to draw a circle through all its vertices. So you know that if the shape is circumscribed in a circle, then all its vertices are equidistant from the center of the circle. That's what it means by definition. And I knew that there must be something for my triangle from my previous proof.
Right.
So this was basically saying from the previous proof, I can take this picture that we started with and stick it right there, erasing the lines I don't need. But what I needed was a circle and the point O going through the points A, B, C. Although I guess I labeled them a little bit different.
Right.
Anything else? Okay. Let's go to 11.3 then. One of you guys want to pull it up and read it for me?
OP,
One second. 11.3. Okay, go.
if OP is the radius of a circle with center O, and the line L passes through P and is perpendicular to OP,
One sec. With center O, comma, and
a line L passes through P, and is perpendicular to OP, comma, then L has exactly 1 point in common with the circle.
Okay. So let's understand this one. What's it saying? So kind of draw a big circle here. Help us see it. So I've got a circle centered at O. We've got a circle centered at O, and it has a OP is a radius of the circle. So P is some point over here on the circle. So OP is the radius of the circle. Right?
Yes.
Okay, yeah.
OP
Okay.
is the radius of the circle.
Now L is a line perpendicular to OP that goes through P. So I know L goes through P and is perpendicular to OP. Here's L. I'm trying to prove that L only intersects the circle at one point.
Okay, yes.
Or in other words, is tangent to the circle. That's what it means for a line to be tangent to a circle. It means it only intersects it at one point. You with me?
Yeah.
Okay, we're going to do this proof by way of contradiction. So assume by way of contradiction what?
That it doesn't, that it intersects more than one.
That it intersects the circle at more than one point. Perfect. Why isn't the contradiction it intersects a circle at no points?
Because it's obvious it does.
Because it was given that L has to pass through P, and P is already a point on the circle.
Right.
So we already know going through no points is impossible. We're arguing that that's the only point it goes through. The contradiction to that would be, no, that's not the only point that it goes through. It goes through some other points.
Right.
So we assume by way of contradiction.
I have a question.
Go ahead.
What is that? L what?
Oh, good question. Let me draw that a little bit better. L is perpendicular to OP. That's the symbol for is perpendicular to.
Okay.
This is parallel to. L is parallel to OP, if we want to say it was parallel.
Okay, yeah.
Okay.
How do we know it's? Oh, okay, never mind.
So now we're setting up an impossible picture.
Yeah.
So we need to argue why this picture is impossible. So assume by way of contradiction that L intersects the circle O at more than one point. We'll call the second point A. Here's the second point that intersects the circle at.
Okay.
Now I know that L is perpendicular to OP, which means that this is a right angle and this is a right angle.
Right.
Okay.
All right?
Okay.
Now, look at this triangle OPA and see if you can figure out why this triangle is impossible.
Because they're both right
Because
angles.
A.
This over here is a right
No,
angle?
it's not. Because
In order for it to be perpendicular, it has to be both right angles in both of the.
No.
How do you know that?
Triangle
No,
can't
that's
have two
not
right
true.
angles.
How do you know that should be a right angle?
it's not supposed to be right angle. It
It's
should
not
be.
supposed.
Well, you just said that the perpendicular line is two right angles.
This
sides.
line is perpendicular to this. We didn't say that this is perpendicular to this. What do I know about OP? It's the radius of the circle, right?
Yes.
What do I know about OA?
It should be the radius.
It also has to be the radius of the circle. A is the other point on the circle
Right.
that L intersects.
Right.
So I know that this is congruent to this. Right?
Yes.
That triangle is congruent.
It's a nice isosceles triangle.
It's a nice isosceles triangle, which means what?
The base thing
The
should be the
base
same.
angles have to be the same.
So that should be right angle.
So that has to be a right angle.
And it can't.
And that's how you argue it has to be a right angle.
And it
Because it's an
can't.
isosceles triangle.
Can't be right.
And why can't it be a right angle?
Because
If you have a right angle, the other two.
if you have a right triangle, the other angle has to be acute. Both the other angles have to be acute.
That's one way you can say it. If you have a right triangle, the other two angles have to be acute. One way you can say it is that the exterior angle is always larger than its opposite interior angle. But that's 90, that's 90. Another way you could have argued it is the Pythagorean theorem. If that's a right angle, then this is a hypotenuse. So this side has to be bigger than that side. We could have ignored the fact that that's a right angle. If that's a right triangle, this side, the hypotenuse, has to be longer than that.
Right.
And yet it's congruent to it.
Yeah.
Contradiction. So a bunch of ways you could have said a contradiction from here. I think most of you want to jump to the fact right angle, they're bad. So that's a good way to say it.
Right.
But the way that you argue that's right angle is because this is an isosceles triangle. Good?
Yeah.
So therefore, that's an impossible picture. So assume by way of contradiction, L intersects at more than one point, call the other point A. Then you get this isosceles triangle. Then you get both their base angles or right angles, contradiction.
Right.
Because we already proved one of our theorems, if a right triangle has its other two angles acute.
Right.
Earlier theorem. Maybe that was a homework problem, but I think it's a theorem. Either way, it's knowledge that we can call upon. Okay, you good on that one?
Yes.
Yeah.
Okay,
What is this section about?
this section is about circles and regular polygons.
Just everything about.
Just everything about it. Just lots of things about it. What we're working up, mostly what we're focusing on in this section is circles and properties of circles. One of the big things we'll be coming to in this section is pi. The number pi. And a definition for what pi is. and we'll be going over how to come up with the area of a circle and the circumference of a circle. A bunch of your circle formulas. Okay, that was 11.3. 11.4, converse to 11.3. All right, so 11.3, let me rewrite it just with very simplistic notation so we can understand what theorem 4 is asking us to do. What we just barely showed here is that if L was perpendicular to OP, then that implied L is a tangent.
Now we're saying L is a tangent, now we know that L is perpendicular to P.
Exactly. So now, theorem 11.4 is saying we need to do the converse of this. We need to show that if L is a tangent, then L is perpendicular to OP.
Okay. Yeah.
And I think,
You're just flipping it.
yeah, we're proving the converse. Or in other words, we're proving that in here we could have said, well, we worded it bad, but this could have been stated as an if and only if. Unfortunately, I can't replace one with the if and only if. Maybe I can. OP, no. I don't know how to quickly rephrase it as an if and only if. But so we're going to prove the converse. We're going to show that if L is a tangent, then L is perpendicular to OP.
Right.
You with me?
Yeah.
Now we're going to prove this using contrapositive. Remember the contrapositive? What's the contrapositive of alpha implies beta?
Beta implies alpha, isn't it?
Beta implies alpha is the converse.
Oh.
And that says something very different.
Alpha does not imply beta, right?
Alpha does not imply beta?
Not alpha,
Not alpha
beta.
implies not beta.
Not alpha implies not beta?
Not beta implies not alpha.
Or is it not beta implies not alpha?
It's not beta implies not alpha.
Are you guessing? We can come up with words really quick just to help us think about it. Let's think about a quick implication here. If I'm wearing shoes, then I'm wearing socks. Means, if I'm not wearing socks, then I'm not wearing shoes.
Yes.
No. It means
Yes.
if I'm not wearing shoes, then I'm not wearing socks.
No.
No. This says, if I'm wearing shoes, I'm for sure wearing socks.
Oh, I thought you said that the other one.
If I'm wearing shoes, then I'm wearing socks says the same thing as, if I'm not wearing socks, then I'm not wearing shoes.
Yes.
Yes.
They say the same thing. So just come up with quick statements in your head. You don't need to guess. Just plug something in really quick.
Right.
Make sure you understand it right. Okay, so we're going to use contrapositive. So here's my alpha, right? Here's my beta. Rather than saying alpha implies beta, I'm going to prove not beta implies not alpha.
Okay.
Right.
So I'm going to show that if it's not the case, that L is perpendicular to OP, then that's going to imply that L is not tangent. Make sense?
Yeah.
Yes.
Okay, so let's get our picture for this. So we're going to pick our circle. Here's our point O. This time we have L is not perpendicular to OP. So here's P. Here's O. And L is a point through O that is not perpendicular to OP. So maybe I'll draw it like this. Here's my L. There's my picture so far. What am I trying to prove? So I know that L is not perpendicular to OP. What am I trying to prove?
L's not tangent.
I'm trying to prove that
That L is not tangent to O. What does that mean?
means there's only one point that intersects.
That's what it would mean to be tangent, so what am I trying to prove?
That it intersects more than one point.
It intersects at more than one point. So I'm trying to prove that there's some other point out here where L intersects my circle. If I can prove that, then I'm done.
Right.
So that's what I'm about to do. Okay, so we've already shown how to prove that if you have a segment well, here's the best, how can I say this? I am going to let M be the line perpendicular to L that goes through the point O. This was one of our constructions we did a while back. If I were to give you a line and a point not on the line, then you can construct a perpendicular to this line that goes exactly through that point.
Right.
That's what we're going to do. So here's my line, OP.
Okay.
Oh, sorry, here's my line L, and my point's going to be O.
Right.
So there exists a line perpendicular to L that goes through O. I'm going to call that M. So here's M. And it extends this way as well, but I don't really care about that much. And since M intersects L, we're going to call the point that they intersect A. So I know this is a right angle, and this is a right angle.
Right.
With me so far?
Yes.
Okay, remember, we're trying to find this other point and argue that's also on the circle. Then L isn't tangent to the circle. It intersects at more than one point. That's big picture where we're going. You with me?
Yeah.
So I'm going to take this distance right here, AP, and I'm going to measure that same segment over here and call the point over here B. My argument is going to be that B is also on the circle. And if I can argue B is also on the circle, we're done.
Right.
How do I argue a point is on the circle?
You show that it's the same distance from the center.
Perfect. I need to show that its distance from the center is the radius.
Right.
Or in other words, I need to show that this is congruent to this.
OP.
So how can I argue OB is congruent to O? OB is congruent to OP. How can I make that argument? How can I argue OB is congruent to OP? Look at the picture. What do you see?
They're congruent triangles.
How do you know?
Side angle side.
Side angle side. Because this side is congruent with itself.
Yeah.
So by side angle side, this triangle is congruent to this triangle. So this length is congruent to this length.
Therefore, B is on the circle.
And therefore, B lies on the circle. And there we go. L intersected the circle at 2 points. Make sense?
Yes. Yeah.
Yeah.
And now we could come up with a quick argument for the fact that no other points in between them lie on the circle. Because, well, let's not say that one too quickly. I think I'll confuse you more than I'll help you. Never mind. So, we'll leave it at that for that one, but there we go. So we just barely proved if it's not perpendicular and it goes through P, then it's not a tangent line. There had to be some other point that it intersected.
Right.
Good?
Yeah.
All right, what's our next one? 11.5. Oh, first we have definition 11.3. A circle is said to be inscribed in a regular polygon if it's tangent to every side. Okay, so
we skipped definition 2.
we skipped definition 11.2. That was just a definition of tangent.
Right.
I gave it to you at the same time in that theorem. Okay. So definition 11.3 is what it means for a circle to be inscribed in a regular polygon. Let me use a square as an example really quick. So here's my regular polygon. There's a circle circumscribing the square. That's a circle that goes through all of its vertices, right? And so that circle, roughly speaking, looks something like this.
Right.
Now we're defining what it means for a circle to be inscribed in a regular polygon. A circle is inscribed in a regular polygon if it's tangent to every side of the regular polygon. So it's going to be tangent to this side, it's going to be tangent to this side, it's going to be tangent to this side, and it's going to be tangent to this side. And so that circle is going to look something like this. So this is the inscribed circle, this is a circumscribing circle in the regular polygon.
Right.
We call the distance from, turns out both those circles are going to have the same center. I think that's going to be one of our proofs, but keep going for the sake of discussion here for a second. we call the distance from the center of the circle all the way to this outer circle, we call that the radius of the regular polygon. And we call the distance to the inner circle the apothem of the regular polygon. So the apothem is the radius of the circle that you can fit inside of it. The radius is the radius of the circle that you can fit it inside of for the regular polygon. Make sense?
Okay.
Yes.
Yeah.
Alright, so tell me, what is the properties of an inscribed circle? If I tell you a circle is inscribed in a regular polygon, what do you know?
That it has an apothem.
I know that the perpendicular bisectors of each side of the polygon are going to line up to the center.
What is the definition of a circle being inscribed in a polygon? It means it's tangent to each of its sides. That's what it means.
Right.
What does
Let's
it
say
mean?
there's 1 point, there's 4 points, no.
There's 1 point on each side of the polygon that the circle touches. One and only one. It doesn't go through 2 of them. So in other words, let me draw
Does
the...
that mean every polygon has a, so,
We're going to prove every regular polygon does. Not every polygon, but every regular polygon. Let me give you one right out the door. There's a polygon. You can't find a circle that contains all those vertices
yeah.
around it, and you also can't find a circle inside of it that's tangent to each of those sides.
Right.
So, what does a circumscribing circle do?
It's
Circumscribed
tangent to every
goes through
point
every
inside
vertex.
the regular polygon.
The circumscribing circle contains every vertex. Okay, and what does the inscribed circle do?
Contains every midpoint. Oh,
It touches.
It turns out it's going to be
tangent every
midpoint,
line.
but we don't know it yet. It's what?
Tangent to every line.
It's tangent
To every
to
side.
every side of the regular polygon.
Right.
Now, it turns out the point it's tangent to is the midpoint, but we haven't proven that.
Okay.
But by definition, it's tangent to every side. Okay, we got the definition of inscribed and we got the definition of circumscribed. So our next proof here is there is a circle inscribed in every regular polygon. So I think this is 11.5.
Yeah.
There is a circle inscribed in every regular polygon. Okay. For the regular polygon I may choose for this one is I may choose just a hexagon, but there's nothing special about a hexagon, obviously. So for the sake of my picture, try and draw a half-decent hexagon just to help us clearly see things. Okay, so I start out with some regular polygon. What do I already know about my regular polygon?
That all the sides have the equal length.
So I know all the sides are equal length, and I know all the angles are congruent, but I also know that
That
There's a circle that
there's
describes every verse.
perfect. I know it has some circumscribing circle centered at O. So there is some circle that contains all the vertices. Okay, what are we trying to do? We're trying to argue that there's also a circle that contains, that's tangent to every side of the shape.
Right.
So let's start labeling some points, A, B, C. I can take, let's see, does he start by labeling the midpoints? No, he doesn't. Okay, I think we're doing the same. Okay. Now, I'm going to choose, I may arbitrarily pick, somewhat arbitrarily pick a couple points here. I'm going to pick the midpoint of this, which I'm going to call the point ABC. We'll call, maybe we're going to want that to be D. So call its midpoint E, call its midpoint F, call its midpoint G, and then do the circle. That gives me a triangle. Do the circle that contains those 3 points. I think I want to do. Let me see really quick to make sure I'm not just going way off a tangent for what he does. Let O be the circle, let AB be the side of the polygon, and C be the midpoint. OC is perpendicular to AB, the circle with center at O. Circle with center at O, radius OC is tangent to AB. We'll just take this one step at a time. Okay, so here's the first thing I want to do. I want to take one of my sides and drop a point down here to its midpoint. So I know that E is the midpoint of A and B. E is the midpoint of A and B. What is E? Hello, are you guys awake? You here? Put the phones away. What is E?
E is the midpoint of B and A.
E is the midpoint of A and B. Ah, there we go. We got an answer. Okay, what am I trying to argue? We're trying to come up with an inscribing circle. So ultimately, I'm going to show that there's a circle. It's going to contain all the midpoints, like Julian was saying. And I need to argue that's tangent to each of those points, right?
Yes.
I'm going to be using the previous proof to do that. How can I argue that the circle centered at O with radius OE is tangent to this line AB? What's one way I can now argue it's tangent using our previous proof? I need to show that this is perpendicular.
Because it.
That was our previous proof,
Yeah.
right? Let me draw out the circle that we're going to be arguing for, and I'll try and draw it in red. So the circle we're going to try and be arguing for is the circle. Sorry, not drawn the best. But red is a circle that we're going to be arguing exists. That's what I'm going to try and bring into existence. I know that there's a circumscribing circle. I'm arguing that there's also this inscribed circle in red.
Yeah.
That's where we're trying to get. Okay, so I'm trying to get there. I'm going to construct this circle with radius OE, which we're going to call the apothem of the regular polygon. So I'm going to construct that circle. That's what the red circle is. I need to argue that this circle is tangent to the line AB. How am I going to make that argument? The way I can argue that is if this is a right angle. That was from the previous proof. If a line is perpendicular to a radius, then it's tangent. So I need to argue that this angle right here is a right angle. So that's where we're trying to get. So here's my shape so far. I need to get that this thing right here is a right angle.
Yeah, okay.
All right, so how are we going to go about doing that? Maybe move O here so we can draw some other lines. Let's drop these lines really quick here. What do I know about these two lines?
They're congruent.
They're congruent. So I know that this is congruent to this. Perfect.
Okay.
Now what else do we know?
Now we know.
That
We know
O to E is congruent to itself, so we have a side, right?
Perfect. I know that this is congruent to itself, and I chose E to be the midpoint of this thing over here. That was my choice of E.
Yeah, so A.
So by side, 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 those two triangles are congruent. What is this angle plus this angle? A straight angle.
Straight angle.
So by definition, that's a right angle and that's a right angle. Right?
Yes.
Yes.
Perfect. So now I know that this point, or sorry, this circle, I know red circle is tangent to that side. Now I need to argue that this point is also on the circle.
You just repeat.
Well, no, because I chose the circle to go through E. That was by construction. I said, now let's pick O as our center, and we'll use radius E to draw a circle. So I used E to draw my circle. So I don't know that F is on the circle. I can't just repeat my proof because that would be drawing a new circle, and I don't know that I'm drawing the same circle.
Right.
So from here on out, I need to argue now F is on that same circle, and it's also tangent. And this is also tangent. And then you can repeat the proof for each of the sides. So the remainder of our proof now is to try and prove that F is also on the red circle. So how am I going to argue that F is on the red circle? And once again, by choice, I've chosen that to be the midpoint of B and C. Which means, once again, I know that this side is congruent to this side, but since this whole segment is congruent to this whole segment, this is actually, that is the same as that, is the same as that, is the same as that.
And O and C are the same as OB.
And we can also drop this line down, and OC is the same as OB, da da da. Perfect. We can also drop this line down.
But we don't know it's congruent.
So we don't know that this is congruent to this. We've got to argue that. That's what we're after.
Yeah.
We have to find.
We know that FBE is the same as, we know that
F,
B is the same as A.
B, E. We know this whole angle, is that what you're saying?
We know that whole angle is congruent to, we know that, basically what I'm saying is B is congruent to A.
You're saying this
We know
angle
that
right
all
here.
those angles are the same, yes.
Yes, we know that this angle is the same as this angle. And that's exactly the same way that we talked about up here.
Yeah.
We now know that these lines bisect those angles. We saw that in this proof. So perfect. So I can say that angle is the same as that angle. So now what?
Now, since OC and OB are the same thing, that means the interior angle of C would be congruent to the interior angle of B. Like,
I've lost it.
so
Since
OC
OC and
OCB is also isosceles, so therefore,
Oh, you want to say this angle's the same?
yeah.
Okay. Didn't really need that, but that's fine.
Oh, I didn't need it. Well, now I got something to say.
Now we got side angle side. So now I can argue that this is congruent to that. So F is on the red circle.
Wait, how'd you find F was congruent to B? Sorry.
Alright. Let's try and reset this up a bit. Well, I don't know if we need to reset it up. Let's just kind of erase what we were working with. So erasing kind of some of this. Okay, so I chose F to be the midpoint of B and C. That was my choice.
B and yes.
So I chose F to be that midpoint.
Exactly.
Now since CB is the same big as AB, because it's a regular polygon,
Yes.
then half of CB is the same as half of AB. So I know that segment is the same as that segment, is the same as that segment, is the same as that segment.
Right.
That's how we got that.
Which would mean it would be exactly.
Well, we'll keep working up to it. That was one piece of it.
Okay, yeah.
The other piece we got is this line OC. That is using the green circle.
Yes.
And so this is the same length as that, is the same length as that. Now drop this line right here, because we're going to be looking at this triangle here. So this is a triangle that we're interested in, sorry. Now, the last piece of information that we need to argue for is that this angle was congruent to this angle, which is the same reasoning we use over here.
Wait, that. Are you sure?
Yes, this angle is congruent to this angle, is congruent to this angle, is congruent to this angle. All those angles are congruent. That is information that we get from the proof over here. When we drop these verticals down from the center, then it perfectly bisects the angles. It splits them perfectly in half. And so since the whole angle is equal to the whole angle, then half of the angle is equal to half of the angle. And so now, by side, angle, side, these two triangles are congruent. So I know that this triangle is congruent to this triangle.
Yeah.
Which means this side length is congruent to this side length. Now this was the radius of our red circle. This was the radius we used to construct our red circle. We said, here's our center. We came out to this point and we used that on our compass to draw our circle.
Yeah.
So, if OE is the radius of our circle, and that segment's the same big as that segment, what do we know about F?
OF is linear, it's the same length.
OF is also the same length, so F is also on the circle. The distance from F to O is the exact same as the distance from E to O. So they're both on the red circle.
Right.
We constructed the red circle using the point E. So we already knew E was on the red circle. Now, since the distance from O to E is the same as the distance from O to F, F also has to be on the red circle.
Right.
And then you can repeat from there.
Almost. Last thing we need to argue is and. That's right angle, because congruent. And so this is tangent to it.
Yeah.
And now we can repeat from there. Now you can use the same argument over here for G as the midpoint over here.
Okay.
And for H over here. Going all the way around. It's always going to be the midpoint, and it's always going to be tangent to it. So now we proved exactly what you said. The inscribing circle goes through the midpoint of all the sides.
Yeah.
So it's tangent to all the sides, and it's tangent at their midpoints.
An inscribing circle goes through all the midpoints of every side. A circumscribing circle is every vertex.
Perfect. Which one's bigger, the inscribed or the circumscribed?
Circumscribing.
The circumscribing circle. Perfect.
Right.
All right. So there is our inscribed polygon. Definition 11.4. The center of a regular polygon. Okay. So now we proved not only is there a circumscribing circle and an inscribed circle, they have the same center.
Right.
So we call that the center of the polygon. So what do I mean by the center of a polygon? I mean draw the circumscribing circle around it and find its center. Or draw the inscribed circle inside of it and find its center. Since those are the same points, the same centers, those are the same. That's what we mean by center of the circle. What do we mean by the apothem? The apothem is the radius of the smaller circle. It's the red radius. And by radius, we mean the radius of the green circle. So a regular polygon has an apothem, and a regular polygon has a radius.
Okay.
Let me draw this void of any picture just to help you see it. So I'm going to draw a square. Really quick, what's the center of the square? It's if we were to draw a circle around it,
Right there.
wherever that point would be. There's the center of our square. What is the radius of our square? Kind of a funny question. It's the distance to one of the vertices. That's the radius. What's the apothem of the square? It's the distance to the midpoint
Right.
of one of the sides.
Okay.
Okay, so that's what definition 11.4 is explaining. Radius, apothem, and center of a circle.
Can you use like the radius? Can you use an apothem to find an area?
We will use apothems to find areas.
Apothem is just another word for radius.
It's a different type of radius. It's a particular type of radius for a polygon.
What's a whole apis? Like, not apis.
Apothem.
Apothem.
Apothem. Like, you know how a full radius is a diameter?
Well, that's not a full radius.
I know, but from
So we have a name for two radiuses together called a diameter.
Diameter.
We don't have something similar for the apothem.
We should do that one.
Okay, so got that. What's our next proof?
0 and 6.
Two regular polygons are similar if and only if they have the same number of sides. Okay. Let's see. We can scribble that over here, I guess. So this was 11.6.
Yeah.
So 11.6. Two regular polygons are similar if and only if they have the same number of sides. Okay. First off, what does it mean for two polygons to be similar to each other?
Is it it's
It's like
So
triangles.
let's-
It's like similar triangles. They're just
Draw a picture
zoomed in
really
or
quick.
out, basically.
Let's draw a picture really quick to help us think about this.
it's for all the angles to be
And we'll do a bigger one.
congruent. All the angles have to be congruent, and the length of the sides has to be.
No, length. size.
Not the length of the sides,
has
but
to be proportional to.
that's the sides have to be proportional. But yeah, perfect. You got it. Two things have to be the case. All the angles have to be congruent, and all the side lengths have to be proportional to each other. Right? That's what it means for two shapes to be similar. Now we're saying two regular polygons are similar if and only if they have the same number of sides.
Wait. So if they have the same number of sides.
So here's two regular polygons. Since they have the same number of sides, they have to be similar. That's what we're saying. So one way of this is trivial. Two regular polygons are similar if and only if they have the same number of sides. First off, if two regular polygons are similar, they have to have the same number of sides because all their sides are proportional to each other.
Right.
So this direction of the proof is completely trivial.
The other direction is a little harder.
The other direction is a little bit harder.
Not a lot.
Not a lot.
It's just saying that that's the only reason. That's the only thing that makes them similar. Right?
No, they're angles.
So in order for them to be similar now, we have to prove that all their angles are congruent to each other and all their sides are proportional to each other.
If they have the same number of sides.
If they have the same number of sides. So here's two regular polygons.
Isn't that understood? Because the definition of regular polygons is same length of sides, or proportional sides and same angles.
Right, so I know that this is congruent to this, 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 and this is congruent to this, is congruent to this, is congruent to this, is congruent to this, is congruent to this.
Yeah.
And that is congruent to that, is congruent to that, is congruent to that, is congruent to that, is congruent to that. And that is congruent to that, is congruent to that, is congruent to that, is congruent to that, is congruent to that.
Well, it'd be congruent to the big one. The angles would at least, right?
We gotta argue that. That's not given to us just because of regular. We haven't yet proved that somehow making a regular polygon smaller or bigger affects its angles.
We have a reason of polygon definition.
Of a polygon?
Yeah.
Yeah, so we had the notion of a polygonal chain.
Okay.
So a polygonal chain is take a bunch of vertices, take a bunch of points, connect them with edges,
I mean a regular
line
polygon.
segments.
A regular polygon.
Oh, a regular polygon. A regular polygon is a polygon where all its sides are congruent to each other and all its angles are congruent to each other. So this is a regular polygon and this is a regular polygon
Right.
with the same number of sides.
You want
I
to-
do not know yet that this angle is congruent to this angle. That's an argument I have to make.
Right.
That's one of the two arguments I have to make here. So I have to argue that all their side lengths are proportional to each other and that all their angles are congruent.
Right.
So kind of drew these close to each other, so we'll just label a couple points on it. I'll call this a point A, B, C, and I'll call this a point A prime, B prime, C prime. You with me?
Yeah.
Now, I already know that whatever A prime, B prime's length is, divide that by AB's length, I already know that that is going to be equal to B prime, C prime length
Right.
over BC
Wouldn't
length.
it be?
How do I know that this is always going to be equal to that?
Because
Because it's a
Because
polygon,
A
so
prime-
they're
A-
the same.
That length is identical to that length, and that length is identical to that length.
Right.
Why isn't it? Why
It's on the
isn't
side of
it?
BC over B prime C prime.
Oh, why didn't we flip the reciprocals on all these?
We could.
I'm saying, why isn't it the big one over the little one?
Completely arbitrary.
Doesn't, you don't need to. You
If-
can flip it.
If 1/2 is equal to, give me anything 1/2 is equal to.
204.
2 over 4 is that's 1. How about we try 50 over 100? Something like that.
2 over 4 is 1.
No.
It's
Oh,
half.
it's 1.
It's 1/2.
Yeah.
So if 1/2 is equal to 50 over 100, flip all the reciprocals, then 2 over 1 is equal to 100 over 50. So yeah, I can flip all those and it doesn't change anything.
Oh, okay.
Just another way around it. And I could say is equal to dot dot dot, and I could do it for all its side lengths, right? Because all the side lengths are the same exact numbers.
Right, because there's only 6.
So we showed all the side lengths are proportional to each other.
Right.
That was trivial. You see it? Yeah. Now we gotta prove that their angles are congruent to each other. So here's what I know.
We need to make a bunch of triangles that are similar triangles. Right?
I know that angle A prime is congruent to angle B prime, is congruent to angle C prime,
And so forth.
is congruent to dot dot dot.
Right.
Similarly with angle A is congruent to angle B, is congruent to angle C, is congruent to dot dot dot. And so, if I were to add all these up, angle A prime plus angle B prime plus angle C prime plus dot dot dot, that would be the same thing as n, the number of sides I have on my polygon, times however big angle A prime was. Just picking one of them. I may as well have just added up A prime plus A prime plus A prime n times. N in our case, in this picture, is 6. N is however many sides my regular polygon has. You with me?
Wait, how do you get n?
N is just however many vertices I have.
Oh, it is.
That's what I mean by N.
thought
I
you
drew
said
6
side.
over here, but this is true for an 8-sided figure, for a 50-sided figure, for a 2,000-sided figure.
Right.
I'm proving it for everything.
Do the number of vertices tell you how many sides there are?
Yeah, there's one side for every vertice. The number of vertices and the number of sides are always the same. A triangle has 3 sides with vertices. A square has 4 sides, 4 vertices. A pentagon has 5 sides with 5 vertices.
Okay. Okay. Yeah, I got you.
Make sense?
Yeah.
So n you can think about as the number of sides or as the number of vertices, same thing.
Okay.
So if I were to add up all this thing's angles, then that would be n times the size of one of the angles. Doesn't matter which one you choose, since all the angles are the same size. If I did 30 degrees plus 30 degrees plus 30 degrees plus 30 degrees 100 times, that's the same thing as 100 times 30 degrees. Make sense?
Yeah.
Losing you? Or does that make sense? Similarly, angle A plus angle B plus angle C plus dot 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 would be the same thing as n times angle A.
Right. Because they're all congruent.
They're all the same side. All the same size, exactly.
Right.
So just adding all n of my vertices up is the same thing as n times the size of just one of them.
Right.
Now, think back to this. What is the angle sum of a triangle?
The angle sum is a straight angle.
One straight angle. So we're going to do 1s for that. One straight angle. What about for a square?
2 straight angles.
2 straight angles. What about for a pentagon?
How many other sides, right?
Yeah.
Oh,
Is it-
pentagon is
Is it 3?
3 straight angles. And you might remember that we proved, going back, because how do we do this? Remember we said you can split this into 2 triangles, so 180, 180.
Right.
This one you can split into 3 triangles. So one side, one side, one side, or 180, 180, 180. So 3s. And in general, if you have an n-sided polygon, so over here, our n is how many sides we have, so this was 3, 4, 5. And in general, if you had an n-sided polygon, then the angle sum was n minus 2 times s.
Can't you split a polygon into more than 3 angles, or 3 triangles?
Not without double counting angles somehow. We only want to add up these exterior angles. And notice that with the way I have it drawn, those angles are exactly all the angles of the triangle. If I were to add another line, like what you're thinking, so you're thinking we could have the triangle here, we could have the triangle here, we could also have the triangle here, right?
And top to...
So now we have tons of triangles there. But now a bunch of the angles of the triangle, if we were to add up their angles, like those angles, those aren't in any way contributing to what we were trying to add up, which is these exterior angles. All I care about is what I'll mark in red.
Oh, just the exterior.
All I cared about was that angle, plus that angle, plus that angle, plus that angle, plus that angle. Right? I didn't care about all those interior ones. So if I'm not going to get any crossing like that, I need to draw my triangles like this.
Based off base angles, right?
Kind of. We just need to make sure that none of our triangles are overlapping onto each other. None of the interior lines are cutting each other. You see?
Yeah.
Okay. So anyways, we already proved that for any n-sided figure, when you add up all its interior angles, it comes out to n minus 2 times a straight angle, or times 180 degrees if you want to think about that way. That's what the angle sum has to be when you add up all the angles. Right? It doesn't matter what kind of pentagon you did. It doesn't matter if it's a regular pentagon or not. As long as it's still convex, they have to be convex shapes. But it doesn't matter if this is convex or not. Its angle sum will always come out to 3s. It doesn't matter that that was a square. It could have been a rectangle. It could have been some sort of trapezoid. It could have been some sort of parallelogram. Its angle sum would have still been 2 straight angles.
What's the angle sum?
The sum of this angle, plus this angle, plus this angle, plus this angle.
Oh, so it's 360.
The sum of its interior angles. In this case, it's 360.
You're saying n being the angles minus 2 times the size.
N is the number of sides.
Yeah.
So 3 sides, your picture looks like this. 4 sides, so here's my n's. This is my n column. If it's 3, here's my angle sum.
Oh. Oh. Okay, I got you.
You guys starting to remember this proof?
Yeah,
It's a really neat one, so I don't mind spending a little bit of time reviewing it.
I remember it. Yeah.
Okay, so now come back to this. Here I have an n-sided figure, here I have an n-sided figure. What is the angle sum of this?
Angle sum is the
4s.
same amount.
4s for this concrete one that I drew,
Right.
but remember that I happened to draw a hexagon. It could have had 100 sides. So in general, what's the angle sum of this thing?
N minus 2s.
So I know that whatever the sum of all these angles is, it has to be n minus 2
Times s.
times s. Similarly, this has to be n minus 2 times s. More importantly, this sum is equal to this sum.
Right.
So divide both sides by n, this angle has to be equal to that angle, or congruent to it.
Right.
That was the argument there. And so all their angles are actually congruent to each other. So now we know that.
So you should
So
use
they
another proof
equal
for
the
this.
same thing.
Huh?
You should use a different proof as your logic for this proof.
Well, the logic of this proof falls back on what we proved forever ago with this.
I'm saying.
They,
Oh, okay.
It's entirely.
they are similar because they equal the same thing, correct?
These
Because
two
the angle sum is the same.
are similar because all their angles are identical. Congruent, sorry. All their angles are congruent and all their side lengths are proportional. That's what needs to be similar.
Yeah, I'm saying the proof's done, right?
The proof is now done. We proved the two things. We proved all their side lengths were proportional, and we proved all their angles were equal. Or congruent, I mean. You follow that?
Yeah.
What can we do for you?
I wonder if I can borrow a cart.
Yeah, there's 2 in here.
Oh. Have at it.
Thank you, sir.
Yep. Okay. So, that finishes off that proof. Any other questions on that proof?
Is that a DVD player?
Yeah.
Okay.
I think there's also one on this card if for some reason it doesn't work. Okay, so now, I'm not sure if we've already come across this definition, but it's an intuitive enough definition. What is a perimeter of a polygon? If I give you some polygon, what's its perimeter?
It's just
It's the side plus side plus side.
It's the sum of the side lengths.
Right.
Take the length of that side, plus the length of that side, plus the length of that side, plus the length of that side, etc. Okay, so our next theorem here is to prove that the perimeter of a regular polygon, perimeters, okay, the perimeters of regular polygons with the same number of sides are proportional to the radii or their apothems. So let's write this one out. It's got a bit of words to it. I don't know if one of these theorems will help more than the other. This will remind us what the apothem and radius are, so maybe I'll erase what's over here. Okay, this is theorem 11.7, right?
Yeah.
Want to read it to me one more time?
The perimeters of regular polygons with the same number of sides are proportional to their the radii or apothems.
Perimeters of two
of regular polygons.
Regular polygons
With the same number of sides.
with the same number of sides
Are proportional to their radii.
are proportional to their radii
Or apothems.
or apothems.
Working out this book.
Okay. So we've got two regular polygons here. Again, we'll just use hexagons because why not? Try and draw one obviously smaller. Alright, those are meant to be regular. So this one right here, we're going to say its radius is r. We're going to say its apothem is a, and we're going to use p for its perimeter. This one down here, I'm going to use primes. Maybe draw this one slightly bigger so that we have some space here to fit inside of it. This is going to be r prime, this is going to be a prime, and its perimeter is going to be p prime. Okay. The perimeters of regular polygons with the same number of sides are proportional to their radii. Okay, let's think how we want to do that. In other words, I'm ultimately trying to get that, right to the side, I'm trying to get that p over p prime is equal to r over r prime is equal to a over a prime.
Okay.
That's what I'm trying to get. Okay, so let
So
me.
apothems is the radius of the inscribed circle.
The apothem is the radius of the inscribed circle. That is correct. So let me pick which triangle would be best to use here for my picture. So here's R.
So they're saying that
Here's A.
so that here is saying that the the apothem is proportional to the perimeter.
Yeah, we're trying to argue this right here. That the perimeter of the big one divided by the perimeter of the small one is equal to the radius of the big one divided by the radius of the small one is equal to the apothem of the big one divided by the apothem of the small one.
Why radius?
We're just going to show all of these are proportional to each other. It's just a useful property. You instantly know that if you have two regular polygons with the same number of sides, Their radiuses are proportional to their side lengths are proportional to their apothems.
Oh, okay,
So it's just a useful fact that you can use in the future for whatever your proof is.
okay.
So here's where we're trying to get. We're trying to prove this equation here. Here's our picture so far. Right?
Right,
About two regular polygons with the same number of sides.
yeah.
Now, I've drawn two triangles that should be hinting at how we do this. What are we going to argue about these two triangles right here?
Right
The
triangle.
right triangle.
So they're going to be right triangles. And what else?
And
Think back to our previous proof. What was our previous proof? The angles of this thing are identical to the angles of this thing. And I know that a radius bisects the angles. So I know that this angle is the same big as this angle.
Yes. And that other angle is.
Let's push this one step further. I want to just make sure you understand. How did I know that these were right angles?
Because they're perpendicular.
because they're tangent.
Because the apothem was tangent to it, which means it was perpendicular against it. Good. Okay, so you're remembering that. Fantastic. So, and that angle is the same as that angle. That comes from our previous proof. We knew that this total angle was equal to this total angle, and we already know that the radius of a regular polygon bisects the angle. Splits it in two.
Right.
So this is exactly half of that whole thing. This is exactly half of that whole thing. Those whole things are equal to each other. So that's congruent to that. Okay. So now what do I know about this angle compared to this angle?
They're,
It should be perpendicular. Or
should be
proportional.
similar.
They are congruent. This angle is congruent to that angle. Right?
Right.
Because both triangles add up to a straight angle.
Right, right. They have to be perpendicular.
So, right, if you know that two angles in a triangle are congruent, the third angle has to also be congruent.
Right.
Perfect. Okay, so now I know that this triangle is similar to that triangle. You with me?
Yes.
Now, I'm going to label these points here. On here, I'm going to call this a point A and this a point B. And on here, I'm going to call this a point A prime, and I'm going to call this a point B prime.
Okay.
So, since these triangles are similar to each other, what does it mean for two shapes to be similar to each other?
They have the same number. Well, obviously, they have their side lengths are proportional.
I'm sorry, what are you again?
Mm-hmm.
Do you think there's a remote on this cart to the
There's that remote, there's this remote. Haven't tried either of them, so I have no idea. And there's also this DVD player that you could try taking.
I'm not gonna
What
dismantle
that
that. The other DVD player is a Sony. This is a Sony TV remote, but it has no buttons on it, so it shows the DVD, but I can't hit play because
Uh-huh. Is there any in the office?
I'll go and look. Thank you. I'm sorry.
Oh, you're fine. Okay, so what does it mean for two shapes to be similar to each other?
Their side lengths are proportional.
Their side lengths are proportional and their angles are congruent.
Right.
Yes.
In this case, we care about their side lengths are proportional. So in other words, I know that the length of AB over the length of A prime B prime is equal to the length of R over R prime is equal to A over A prime.
And P over P prime.
Now we don't know P over P prime yet. P is this. These are just the three sides of the triangles. I know that the sides of the triangles are proportional to each other. I'm just using the fact that this triangle is similar to this triangle very directly.
Oh, okay. You're
You
not
see
talking
that?
about
If the
it's not that
sides are
triangle.
proportional to each other, don't we know P is proportional to P prime?
How would you make that argument?
No, all we're
Follow
talking
it
about, Alvin, all we're talking about right now is a triangle.
So pretend that this has n sides. Think through your proof. Think through how you would explain it.
The perimeter is the side lengths.
It's the sum of all the side
Sum
lengths.
of all the side lengths.
Okay?
Yes. And if the side length for big triangle is similar to the side lengths for little triangle, or not big triangle.
Well, you're trying to explain too much. Here, just think about this for a second. What is the perimeter of this shape?
it's of that shape right there.
Yes, this shape right here. What's its perimeter?
The sum of all its side lengths.
Right, it's the sum of all side lengths, okay. But notice we have this
It's AB.
right here. So here's the length of
It's
AB.
times 2,
It's
AB squared
2AB
times n. It's 2AB times n.
times the side length.
Times the number of sides,
The number of sides.
which is n. So 2AB gets us this, multiplied by n gets us the perimeter of the whole thing.
Yeah.
So,
2AB prime.
you might remember back to when we were doing our work with fractions, you can multiply the top and bottom of your fraction by the same number and it doesn't change the fraction.
Right.
So this is equal to 2n times the length of AB, and it's also equal to 2n times the length of A prime B prime,
Which is the perimeter.
No.
which is the exact perimeter, P over P prime.
Right.
You see it?
Yeah.
That's the whole proof. P over P prime is equal to R over R prime is equal to A over A prime.
Yeah, okay.
Yeah, that's it. Not bad, right?
Hold up, let me get this camera. Oh, we were trying to prove the perimeter. That the perimeters are proportional.
Yeah, we were just trying to prove this equation right here.
Oh.
That's it. That's all we were trying to do. Okay, our next theorem is we're trying to prove that the area of a regular polygon is some formula, but let's just come up with this formula ourselves. Forget the proof for a second. Let's say I give you some regular polygon and let's come up with a formula for its area. We'll use a hexagon once again as our stand-in for some regular polygon.
We're trying to prove what? Sorry.
We're trying to come up with a formula for the area of this thing. So I give you some regular polygon. It has n sides. So we know it has n sides. We now want to come up with a formula for the area of that polygon.
We can do all the triangles within it, right?
Break it into triangles. So let's break it into one triangle here.
It's half
Well,
base times
maybe
height.
let's break it into triangles and let's see how we can quickly make an argument that all these triangles are congruent to each other.
Okay.
So first off, I know that all these side lengths are congruent to each other, right?
Yes.
We know all the
Because
base
they're all the
lengths.
radius.
All the base lengths are the same.
We know all the base lengths are the same.
And all the angles is.
We don't even have to do any more from there, right?
Yeah.
Right.
Because then by side, 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 all these triangles are congruent. So if I can find the area of one triangle, remember it was one of the things that we were assuming for area that we weren't going to prove, but it's that triangles that are congruent to each other have the same area.
Right.
So the area of our whole, and we had another one that says the sum of the areas gives you the area of the whole thing. And so now I can find the area of just one of these triangles and multiply it by n, and that gives me the area of the whole thing.
Yes.
You with me?
Yes.
Yeah.
Okay. So let's find the area of this triangle right here.
It's 1/2 base times height.
It's 1/2 the base times the height. So we'll do a stand-in once for the base. This is A, this is B. And then we remember that there's n sides. So what is the height of that triangle?
It is the radius.
It's the radius.
No, it's the apothem.
The apothem.
The apothem.
Perfect. So the apothem is the height, and then the base is AB. So I know that the area of this triangle is 1/2 the length of one of the side lengths, AB,
Times the apothem.
times the, I don't really know how you pronounce it. I call it an apothem.
Apothem, I think.
You guys all say apothem.
Apothem. That's
Might be right.
That's how we learned it.
Probably at school.
Apothem.
Anyways, so now this gives us the area for one of these triangles. I want to find the area of the whole polygon, so I just take that and I multiply it by n. Right? And that gives me the area of the whole thing?
Yeah.
Okay.
No.
Yes.
This is the area of this
One.
triangle,
And
Okay, yeah, it should.
and there's n triangles, so that should give me the area of all the other pieces.
Right, okay. Thank you. Yeah.
Okay, you see it. Now, I'm going to rewrite this just a little bit differently. Same expression. Just reordering the terms, right?
N times AB is perimeter.
N times AB is perimeter. So the area of a regular polygon is 1/2 times its apothem times its perimeter. And so, theorem 11.8, the area of a regular polygon is equal to 1/2 the product of the apothem and the perimeter. So that's what it was to prove. Okay, theorem 9. The areas of two regular polygons with the same number of sides are proportional to the square of the radii. And the square of the apothems. Okay, so this time I'm trying to show that the area of one divided by the area of a different one is equal to r squared over r prime squared is equal to a squared over a prime squared. Very similar to what we had up here. You with me?
Yeah.
Now I know that, let's just write it out. I know that the area of any regular polygon is equal to what?
Area of
Any regular polygon is it's 1/2 AB.
Right. So the area of this polygon is going to be 1/2 times its apothem times its perimeter.
Right.
Right? Which the area of this one is going to be 1/2 times its apothem times its perimeter. Now the 1/2s go out.
Right.
So it's going to be proportional to a times p all over a prime times p prime. Now I already know over here that a over a prime is the same thing as p over p prime. So I can replace my p over p prime here with a times a over a prime times a prime. I replace p over p prime with a over a prime. You with me?
Yes.
Which gives me a squared over a prime squared. So I showed a over a prime is equal to a squared over a prime squared. Reset over here, come back to this. This,
But why
starting
do you
with this
get
one.
the- Why do you just take the P out?
I know p over p prime is equal to a over a prime.
Oh, right.
So I did that substitution.
Makes sense.
Now over here, I know a over a prime is equal to r over r prime, and p over p prime is equal to r over r prime. So I'm going to do a double substitution. I'm going to replace a with r, and I'm going to replace p with r. And a with r prime, and p with r prime. So a over a prime is equal to r squared over r prime squared is equal to a squared over a prime squared. This is the formula we were trying to prove. So we instantly just get it for free from plugging in this formula using that. So it's a quick combination of those two. That could have pretty much just been a quick corollary. This proof is left as an exercise to the student. Whoops. Okay. So now we get to limits. Limits, limits, limits. One of the hardest concepts students have to come across unless they go into some sort of advanced degree.
You don't want to do that tonight? You want to do
Oh, did I skip one?
You want us to do that next one?
No, you just did.
11.9. 11.9 is what I just did.
No, we just already did 11.8.
No, that was.
11.9 was proving.
Oh, are they proportional?
Area.
Oh, thank you.
Okay. So now we get to limits. So first, let's just do a quick run through an example of limits before we do anything concrete, just to demystify them a little bit. So I'll start by giving you some intuition, a little bit of demystifying. I'm going to give you some sequence of numbers, and I'm going to develop it in a certain way. So follow the pattern. Look at the numbers 1 over 1, and then 1 over 2, and then 1 over 3, and then 1 over 4, 1 over 5, dot, dot, dot. You see the pattern?
Yeah.
What's the pattern?
Always increasing by one.
Increasing the denominator by 1.
Yeah.
Okay. Question. If I were to follow this pattern out forever, is there a number that it's getting closer and closer to?
No.
Yes.
No, it's getting farther and
There
farther.
is one
from
number,
one.
yes, there exists a number.
What is the number that we keep getting closer and closer to?
0.
So if I were to keep writing this out, I would have eventually written 1 over 1, 0, 0, 0, 0, 0, 0, 0, 0, right?
Right.
And then 1 over 1, 0, 0, 0, 0, 0, 1. And we would have kept writing. And we're getting closer and closer to 0 is what this is approaching.
But never getting there.
It never gets there. But it's getting arbitrarily close to 0.
Yeah.
And so the way we would write this out with calculus notation is we would say that the limit as n approaches infinity of the sequence 1 over n is equal to 0. That's the big bad calculus way of writing that.
What is that? Oh, okay.
The limit as n approaches infinity of 1 over n equals 0. Notice 1 over n is a pattern we have here. You plug in 1 for n, that gives you this. Then plug in 2, then plug in 3, then plug in 4, then plug in 5. And as n gets arbitrarily large or approaches infinity, then this sequence gets arbitrarily close to 0.
It stops at 0.
Well, I don't know about stops. It's not moving, it's numbers.
What's
It's an infinite sequence that we can't write down.
what's arbitrarily? It's basically like useless.
No, arbitrarily is not useless. Arbitrarily is not concrete. Oftentimes when we're doing proofs with a triangle, we say, let this be an arbitrary triangle. And you say, well, you drew it equilateral. Ignore that. We're not paying attention to the concrete features of what I actually drew on the board. It's a stand-in for an arbitrary triangle.
Okay.
When I say that this gets arbitrarily close to 0, what I mean is, pick any teeny tiny number you want. And my sequence will eventually get at least that close to 0. I can get as close to 0 as you want. If I carry out this sequence far enough.
You'll never reach it.
But pick any small distance you want. You say 1/1 trillionth. I say yes, this will eventually get within 1/1 trillionth of 0. You say 1/1 trillionth squared. I say yes, this will eventually get within 1/1 trillionth squared of 0. Pick any really small number you want, and this sequence will eventually get that close to 0.
Right.
Make sense?
Yes.
Let's try another one before we hit reset. So I'm going to give you another sequence. This time, I'm going to write it the big bad calculus way and have you think about it. So this time, let's look at this. Let's look at the limit of the sequence n plus 2 over n. So first off, let's start writing out some of the terms to get comfortable with this thing. So if I plug in 1 for this, what do I get?
1 plus 2 over 1.
3 over 1.
You get
3 over 1.
Therefore 3.
What do I get next?
4 over 1.
5 over 1.
We're plugging in 2 for everything now.
Yeah. So
2 plus 2 over 2.
2 plus 2 is
4 over 2.
4 over 2,
Which is 2 over 1.
Yeah.
which is 2 over 1, but 4 over 2. Okay, what's next?
5 over 3.
5 over 3.
6 over 4.
6 over 4.
5.
And is this getting closer and closer to some number?
Yes.
Yeah.
What number?
Well,
Any number. Right?
It's already bigger than 1.
it's going 3.
It's already more than
2,
1. It's already more than.
something, and then it goes.
Wait, no, it's getting smaller.
Yeah.
It's getting smaller and smaller, but is it getting closer and closer to something?
It's getting closer and closer to 0.
Closer and closer to 0?
Yeah.
Yes.
Yeah.
Yeah? Let's keep thinking. What comes next?
7 over 5.
7 over 5. Let's skip ahead some. Plug in 100, what do we get?
100 over 99. Oh.
102 over 100. Right?
Right.
We getting closer and closer to 0?
No.
Okay,
That's not very close to 0 yet. How far do I need to go to get close to 0?
We're getting closer and closer to 1.
We're getting closer and closer to 1.
Oh, thank you. Yeah.
Right? Let's go down a bit and let's plug in 10,000.
10,000. Yeah.
Writing that out as a decimal, what is that as a decimal?
1.000.
1.0002.
We're getting closer to 1.
Right? And if I were to go out stupid far, then our number, when we wrote it, it would be something like 1.00000000000000. 2, that would eventually be 1, right?
Never reach.
We never
Never
reached
reach
1, but we get arbitrarily close to 1.
Yeah.
And so in the limit, we evaluate that to 1.
Okay, yeah.
So this is just establishing intuition. I'm going to give you the full big bad definition of a limit. This is just intuition. This is just to make you feel good about it, before I make you feel really bad about it. Okay, so that gets you comfortable with the idea of a limit. Now, speaking precisely. So first we got to remind ourselves about sets.
Sets.
Yeah, there's a reason that we had a bit to say about sets early on in the year and talking about sets. So with sets, if I have the set 1, 2, remember that this is the same thing as a set 2, 1, which is the same thing as a set 1, 2, 2, 2, 1, 1. All those sets are the exact same thing.
Right.
Repeats don't matter in sets, order doesn't matter in sets.
Because it's just the numbers.
How do you determine if 2 sets are equal? You say, is everything that's in this set, and is everything that's in this set, in this set? The answer to both those questions are yes. That's what it means for 2 sets to be equal.
Those are equal.
Those sets are equal. They're identical. They're the exact same set. No difference between them.
Wow. Is that
The same way that this is just a different way of writing
What's a
4.
set?
Wait, is that because there's 3 1s and 3 2s?
No,
That was just a coincidence.
that was just coincidence.
Okay.
Still identical.
Because when you have more than one, it cancels out, right?
So what is the set?
More
What does the
than
set
one
entail?
number.
What is a set?
So strictly speaking, a set does not have a definition.
In this case, what would you?
The way that you give intuition for a set to kids is you tell them that it's an unordered, unique collection. Unordered, meaning order doesn't matter. Unique, meaning duplicates don't matter.
Interesting.
But if we were developing set theory from scratch, then a set would be one of our undefined terms, the same way that a point is an undefined term in geometry. Okay, so those sets are identical to each other. Now we have the concept of a list. When we're talking about a list, the list 1, 2 is very different from the list 2, 1, is very different from the list 2, 2, 1. In lists, order definitely matters, and duplicates definitely matter. We use lists to talk about the coordinates of points. The coordinates of the point 1, 2 is very different from the coordinates of 2, 1. It's very different from the coordinates 2, 2, 1. This is in a 3-dimensional space. These are both in 2-dimensional spaces.
Right.
Very different things. So lists and sets. Now we get the definition of the function. What is a function? You're used to from your algebra classes a function being written somehow like this. F of x is equal to x squared, right?
Right.
A function is a set of ordered pairs. What's an ordered pair? It's a list containing 2 things. It's a set of ordered pairs where each left-hand element goes to a unique right-hand element. So here's a set of ordered pairs. It is not a function because I have 1 paired with 2 and I have 1 paired with 3. Can't have that if it's going to be a function.
Okay.
But if I instead replace 1 here with SpongeBob, and so I have 1 goes to 2, SpongeBob goes to 3, and square goes to star, this is now a function.
Because they're unique.
It's a set of ordered pairs where every left-hand element goes to 1 right-hand element. I could have also said SpongeBob goes to 2, and this is still a function. 1 only goes to 1 thing. SpongeBob only goes to 1 thing. Square only goes to 1 thing. Each left-hand element only goes to 1 thing. It doesn't matter that 2 showed up twice on the right-hand side.
But it can't show up twice on the left-hand side.
Can't show up twice on the left-hand side unless I were to make it show up twice on the left-hand side like this. 1, 2. If I put that in again, it's still a function. Because I didn't change my set. Because duplicates don't matter in a set. It's a set of ordered pairs. So if I put the same ordered pair in there again, it doesn't change anything. Make sense? That's a function. You're used to functions like this. This is syntactic sugar. This is shorthand for writing an infinite function. What is this explicitly? If we were to try and actually write out exactly what this function is, we couldn't do it. We'd go on forever. But that is a function. Let's see. 0, 0 is in there. 1, 1 is in there. 2, 4 is in there. Square root of 2 and 2 is in there. Negative square root of 2 and 2 is in there. Pi and pi squared is in there.
It doesn't matter, anything could be in there. Is that what it means?
Not anything could be in there. 1.5 and 2.25 are in there.
What can't be in there?
Everything that's in there, the right-hand thing has to be the left-hand thing squared. It's following a pattern. This is that times itself. 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 This is that times itself.
Right.
I'm writing out this
It
function.
has to follow a pattern?
Yes, that's what this is. You're saying, here's the pattern. You're saying, I'm not, when you see this notation, you're saying, I'm not going to write out all infinite elements. I'm just going to tell you the pattern. And you're going to know whether or not something is in there or not by checking the pattern. So this is shorthand for this infinite set. It's just shorthand. A function is a set of ordered pairs. So f is equal to this. That's our function. This is a shorthand way of writing that information because we can't write out all infinitely many elements. That would take forever. And then some. Right?
Yeah. That's confusing.
Well, you're already used to
I
this.
understand it.
I ask you a question really quick, like, is 1, 7 in this function? Is 1, 7 in that function?
No.
No. I ask you, is 4, 16 in this function?
Yes.
Yes.
Yes. So that's what you're doing. Based on the pattern, you can tell me everything that is and is not in the function.
Right.
The function is a set of all these ordered pairs. When you interpret its ordered pairs as coordinates, then you can plot them on a graph.
Right.
And that's what you do when you graph the function. You're plotting all the points in the function. You're plotting all these points. Those are all the points in the function.
Right.
The function is those infinite points, those infinite ordered pairs.
The function. Yeah.
The function. What's a function? It's a set of ordered pairs where every left-hand element goes to a unique right-hand element. That's it.
Right.
And it doesn't have to be nice, pretty functions like this. This is a perfectly valid function. I have SpongeBob, goes to 2, and I have A, goes to C. There's my function. Perfectly valid function, nothing wrong with it. Not a very useful function, so you don't come across it in your algebra courses or whatever, but still a perfectly valid function. Nothing wrong with it. Function is just a set of ordered pairs. Okay, now we get to a sequence. This is working up to the definition of a sequence because you only take limits of sequences. A sequence is a function where the left-hand elements are all the positive integers. So I have to have 1 goes to something. I have to have 2 goes to something. I have to have 3 goes to something.
This word is what?
This is a definition of a sequence. It's a type of function.
And all the left-hand letters are positive.
And all the left-hand elements have to be all the positive integers. You can't skip any positive integers. 1 has to be in there. 2 has to be in there. 3 has to be in there.
Can't be.
Every single one.
It has to be every single one. Okay.
So how big is the function?
Big.
Infinite. Every sequence is infinite.
Right.
Because it has to pair 1 to something. It has to pair 2 to something. Right?
Right.
And so if we were talking about the sequence we started with, we paired 1 to 1 over 1. We paired 2 to 1 over 2. We paired 3 to 1 over 3. We paired 4 to 1 over 4. We paired 5 to 1 over 5, etc.
It has to follow a pattern, right?
It doesn't have to follow a pattern. But now I have to, just like a function doesn't have to follow a pattern. It can, it doesn't have to. Most sequences we're going to work with are going to follow a pattern, just like most functions you work with follow a pattern. Right?
Okay.
So it doesn't have to follow a pattern. Here's one that does follow a pattern. Since this one does follow a pattern very nicely, then we have a shorthand for it, the same way that we have our shorthand for functions when they follow nice patterns. One way I could have written this, it's not very common notation, but I could have said f of n is equal to 1 over n. That's the pattern being followed,
Yeah.
using functional notation.
Okay.
You with me?
Yep.
A more standard way that we do it is we say something like x sub n is equal to 1 over n.
That's a sequence?
As our sequence. And when we're talking about an arbitrary function, we use f of x as some arbitrary function. I say consider the function f of x. Which function is it? We don't know. It's an arbitrary function. In similar manner, when we're talking about an arbitrary sequence, we'll do x of n like that, and we'll put parentheses around it, or brackets around it like that, to remind us it's a function, or a sequence. And when we want to talk about a concrete sequence, the notation we'll often use will look like, if x of n is equal to 1 over n, if I know what it is, I'll write it like this. So this is how we'll signify our sequences. Shorthand notation. You with me? So let's write out one really quick now. So if I say, let's look at the sequence, n over n plus 2, what exactly is that sequence? If we were to write this out concretely, this is the function 1 goes to 1/3.
3. Oh.
Right?
Yeah. Okay.
2 goes to 2/4. 3 goes to
3/5.
3/5. 4 goes to
4/6.
4/6. And we go on forever. Now I happen to be doing these in order, but remember sets don't care about orders. It doesn't change the sequence if I swap these two. So when we write out a sequence, you and I, we have this agreement. I'm going to write whatever is paired with 1 first. And then I'm going to write whatever is paired with 2. And then I'm going to write whatever is paired with 3.
You're saying 1/3 and 1 is the same thing as n over n plus 2?
When I plug in 1 to this, I get 1/3.
I know, but you said if I switch those, it doesn't change.
Oh, sorry. I'm saying, so imagine I instead came over here, and I said, let's see, and 6 goes to, what does 6 go to?
6 and 6/8. Or 6/8.
And then I said, and 5 goes to,
5 and 5/7.
it doesn't really matter that I wrote the 6 one before the 5 one. Inside of here, because it's a set and order doesn't matter.
Okay.
I wasn't saying you could swap those. Right, I get how I confused you. But if we agree amongst ourselves, we're going to write whatever number 1 goes to first, and then whatever 2 goes to, and then whatever 3 goes to, and then whatever 4 goes to, then we often just represent a sequence ignoring its left-hand terms.
Because it's an understood, right?
Because it's understood. So it's understood that when I write out a sequence like that, this is what 1 was paired with, this is what 2 was paired with, this is what 3 was paired with. Okay, so that's sequences. Now we can talk about limits of sequences. Limits only make sense when you're talking about a sequence. So what's a sequence? It's a function whose left-hand terms are all the positive integers. That's what sequence is.
Okay.
We can only take limits of sequence. Not every sequence has a limit, but some sequences have a limit. So now, here we go. The big bad definition. And then we'll try and make it make sense. And then we'll start next time by re-going over this definition and trying to make it make sense again. Because it's one of those things that you just got to be exposed to it a few times for it to click. Here's what we say. By definition, the limit as n approaches infinity of some arbitrary sequence, x of n is equal to the number x. We are defining this notation. So what do I mean by that notation? I'm about to define it now.
What is x of n?
X of n, we use x of n for an arbitrary sequence, the same way that we use f of x for an arbitrary function. So this just means some function. Which function? I don't know, just some function.
That's what x.
X of n is a sequence. Which sequence? I don't know, just some sequence. X of n.
Oh, okay.
If we had a concrete sequence, we would write it like this. Here's how we would write a concrete sequence that we knew. If we don't know what the sequence is, it's just an arbitrary sequence, we write like this. Okay? So I'm defining what it means for a sequence to have a limit, and for its limit to be x. What does that mean? By definition, so colon back and forth error. We're defining now. Defining everything over here. I'm going to write out its definition. What does this mean? This means that.
And, oh, that means for every.
For every positive real number.
That means, wait, what is the upside down A then?
Okay. That is for all, like you have.
For all.
For all or for every.
Okay, what is that? I thought that E was for every.
No, so there's for all, and then there exists.
Oh, there.
Those are our two quantifiers.
What is that?
So this is just an epsilon, and it's going to represent a small real number.
Okay.
So we said for every small real number in, this is our symbol for being in a set,
Right.
in the real numbers, but we put a plus up there, meaning we're only talking about the positive real numbers. So this reads for every epsilon in the positive real numbers, or a way that we'd often say that is for every positive real number, there exists some big N in the positive integers such that the distance between x sub n and x is less than epsilon for all little n greater than or equal to big N. Okay, there it is. That is a very big boy definition.
That's the definition of limitation.
Yes, this is the exact definition of what this means. This is a whole definition of a limit. Not sugarcoating anything, not dumbing anything down. This is exactly what it is.
Let's go through it one more time.
Yeah, we're going to go through this a few times to try and make it make sense. We're first going to focus on what this part means and go from there. Okay? So first off, imagine I have 2 points on the number line. Here's a little point A, here's a little point B. What is the distance between the 2 points A and B? How do you get it?
Choose a unit, measure it.
Sorry, what?
Choose a unit and measure it.
Choose a unit and measure it. That's what you do in geometry, but I literally tell you that this is at the point -2, and I literally tell you this is at the point 9. What's the distance between them?
11.
How do you do that?
Absolute value.
You take the absolute value of the difference.
What's the difference?
You take the absolute value of B minus A. In this case, B was 9, and you minus -2, which was equal to 9 plus 2, take its absolute value as 11.
Yeah.
Notice, if I would have instead called this B and this A, this still gives me the distance between them.
Right.
Because if that would have been the case, then we would have said -2 minus 9, absolute value is -2 minus 9 is -11, take its absolute value is 11.
Right.
So either way you get 11, doesn't matter what order you do it.
Right.
So the absolute value of B minus A gives you the distance between those two things. You with me? So up here, we're saying that the distance between these two numbers is less than epsilon. That's the way that you think about that.
Epsilon means.
Epsilon is going to be some small positive real number. So let's take this kind of pictorially for a second.
So epsilon is what, undefined or what?
So here's x. Epsilon is going to be an arbitrary small number. You'll get used to this here in a second.
So it's just some random small number.
So here is my x, and I've got some sequence of terms that is getting closer and closer to x. So maybe the first term in my sequence, which we signify as x sub 1, since my sequence is x sub n, x sub 1 is the first term, x sub 2 is the second term, x sub 3 is the third term, dot, dot, dot. Make sense?
Yes.
So x sub 1 is right there. X sub 2, maybe that's right there. X sub 3, maybe that's right there. X sub 4, maybe that's right there. And we keep going, da, 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 and we're getting closer and closer and closer to this x value, right?
Do you ever touch it?
Do we ever touch it? Maybe. But we're saying we're getting closer and closer to it.
Okay.
So to do something very concrete, one of the sequences we already talked about was x of n being equal to the sequence. What did we just really do? N plus 2 over n. In that concrete case, x of 1 was equal to 3. X of 2, maybe right this way, 3 over 1. X of 2 was equal to 4 over 2.
3 over 2.
3 over 1, thank you. 4 over 2. X of 3 was equal to 5 over 3. X of 4 was equal to 6 over 4, etc., right? And so this could have been x of 1, x of 2, x of 3, x of 4, getting closer and closer to our x value, which was 1 in this case.
Whatever our sequence was, right?
Yeah, so this is just some arbitrary sequence getting closer and closer to some x value. We already did a concrete case where this was our sequence, and the x value that we were getting closer and closer to in this case was 1.
Yeah.
So in this concrete case, x represents 1, x of n represents this, x of 1 is first term, x of 2 is second term. So we're getting closer and closer and closer to this. What we're saying is, this sequence gets closer and closer to x if, for any small distance you choose, pick any small distance you want, epsilon. You get to give that to me. You get to pick any small distance you want. I can find a point in the sequence where the whole sequence is now that close to x. So let's say that the epsilon you gave me was this big. These are all the points whose distance from x is less than epsilon.
Okay.
You with me? So this point on the real number line is x plus epsilon. This point on the real number line is x minus epsilon. These are all the points whose distance from x is less than epsilon.
Distance from x is less than epsilon.
Let's do something concrete for a second. Let's say that here's x on my real number line.
Okay.
Let's get even more concrete than that. Here's 3. What are all the numbers whose distance is less than 2 away from 3?
Is
Five,
less than
-5.
2 away.
You can go up to 5 and you can go down to 1. All the numbers between 1 and 5, their distance is less than 2 away from 3.
Okay.
So
if
all the
epsilon
numbers
is
from here
2,
to here. So in this case, epsilon was equal to 2 and x happened to be equal to 3.
So everything between x minus epsilon and x plus epsilon is less than epsilon.
Is less than epsilon away from x. These are all the numbers whose distance is less than 2 away from 3.
Will it be less than epsilon? It doesn't even need to be away from x, right?
Uh,
'Cause there's no possible.
let me give you another example. This will clear that up in your head real quick. Let's say that my x is 1,000. What are all the numbers within 2 of 1,000?
1002 and
1,002
198.
and 998. So these are all the numbers. So all the numbers from 998 to 1002, all those numbers are the numbers whose distance is less than 2 away from 1,000. Those numbers aren't less than 2. This number isn't less than 2. This number isn't less than 2. This number isn't less than 2. It's less than 2 away from 1,000. This number isn't less than epsilon. It's less than epsilon away from x. This is more than epsilon away from x. This is less than epsilon away from x.
So epsilon isn't 2, it's 2 from x.
Well, epsilon is a distance. So epsilon is 2. Epsilon is not a point on the plane.
Yeah.
Epsilon is how close we want the points to be to x. So if I want them to be within 2 of x, then epsilon is 2.
We want to be in 6.
If I want them to be within 1 of x, epsilon would have been 1. If I wanted them to be within 1/2 of x, epsilon would have been 1/2. You with me?
Yes.
So here's x. The points between these 2 points, all the points in here are the points whose distance from x is less than epsilon. In other words, if I were to pick this random point right here, little a, I know that the absolute value of x minus a is less than epsilon. The distance a between a and x is less than epsilon. For any point I pick in here, its distance from x is less than epsilon.
Yes. Okay.
Good. You're with me so far. So we start out with some sequence. I want to know, is the limit of that sequence x? Here's the way I test it. You get to give me any distance you want, any epsilon.
6.
6, 10, whatever. Typically you want to pick a really small number, like 1 billionth. Typically we think about it as a really small number. But you give me any epsilon you want. So then I draw out, here's x plus epsilon, here's x minus epsilon. Here's all the points that are within epsilon of x.
Okay.
You with me?
Yeah.
Yes.
Now, what we mean by the sequence converges to x, or the limit of the sequence is x, is there eventually comes a point in our sequence where the entire sequence from that point onwards is within epsilon of x.
Right.
So in this case, here's x sub 4, here's x sub 5, here's x sub 6, here's x sub 7, here's x sub 8, here's x sub 9, there's x sub 10. This one right here, x sub 11. You with me?
Within epsilon.
X sub 11 is within epsilon of x. So is x sub 12, and x sub 13, and x sub 14.
How do you get x plus epsilon? How do you get to that point?
Well, I want to test if my sequence converges.
I'm just wondering, can you even get past x to get to the point x?
Oh, my sequence could have gone a little bit past and a little bit back. A little bit past, a little bit back, getting closer and closer and closer that way.
What do you mean?
So let me give you another one. Concrete sequence for a second. Let's look at the sequence. We're going to do -1 to the n times n all over. We'll do -1 to the n times n plus 2 all over n. Let's look at this one. Okay, so we plug in 1. When we plug in 1, what do we get? 1 plus 2 is 3. -1 to the power of 1 is just -1. So we get -3 in the top and 1 in the bottom. So in this case, it's -3. Right? Now let's plug in 2. 2 plus 2 is 4. -1 times -1. -1 to the power of 2, or -1 times -1 is +1. So 4 times +1 is just 4. And then we're dividing by 2. So now it's +4 over 2.
Oh, that's what you mean.
It can alternate getting closer and closer to the number.
But wouldn't that make x 0? Or
Well, in this case, x isn't going to be 0. What's x going to be? So let's keep writing these out. What's my next one's going to be? Next one's going to be -5/3, and it's going to be +6/4, and it's going to be minus 7/5, and then positive 8/6, and we keep going. Now, actually, this one doesn't get closer and closer to a number, because it keeps getting closer and closer to 1, the -1, 1, the -1, so this one doesn't have a limit.
It doesn't?
No,
If it has more
because
than-
all the positive terms get closer and closer to +1, and all the negative terms get closer and closer to -1. So there isn't one number that is getting closer and closer to.
I see, okay. Yeah, so it wouldn't even have a limit.
So that one doesn't have a limit. Now let's do one more case where it is going to have a limit, and it's going to alternate. So this time,
So you're saying that -7/5 is on the right side of x, and 8/6 is on the left, right? Left.
so that one was kind of a bad example for what I was explaining, because that one ended up not having a limit. I wasn't thinking. So here's one that is going to have a limit, and it's going to jump back and forth. So looking at this one, when we plug in 1, we get -1. Then we get +1/2. Then we get -1/3. Then we get +1/4. Then we get -1/5. Then we get +1/6. And in this case, it is getting closer and closer to 0.
Oh, okay.
So there's one where it jumps back and forth on both sides of x, but
So it
getting
can't-
closer and closer and closer.
It can get past, can't hit that point.
Yeah,
Can't hit its limit.
because I could have taken this sequence, say that it went 1, 6, and then suddenly I had something 10,000 there, and then we continued the pattern as normal. -1/7 plus 1/8. So maybe it's not one that we can write with a nice formula, so it's not this formula, but it's a sequence, and from here on out it follows that pattern. This 1,000 here doesn't change anything. It still is getting closer and closer to 0. And yet that would put a point suddenly clear out there.
Yeah.
Okay, so let's come back to this definition. What do we mean when we say that our sequence converges to x, or that the limit as n approaches infinity of our sequence is x? That means that for any small distance you choose, so you're picking some distance to place around epsilon, there exists an index in our sequence. There exists a positive integer. it's going to be an index in our sequence. In this case, it was 11. There exists some positive number such that from that point in our sequence onwards, our distance from x is less than epsilon. From that point onwards, for any little n greater than or equal to big N.
Okay.
So, let's see that here again. You pick any epsilon you want, right? Let's pretend that the epsilon you chose here was epsilon equals 1/2. Let's pretend that that's what you chose here, right?
Okay.
And we'll pretend that's x plus 1/2, x minus 1/2. What did I do? My job is, for any epsilon you choose, I have to find an index. So I come along and I say, okay, then big N is going to be equal to 11. Because now, x sub little n minus x is going to be less than epsilon as long as you replace that little n with a number greater than or equal to big N. My big N I said is 11. Pick any number bigger than or equal to 11, any positive integer. 12. So I'm saying x sub 12 minus x is less than epsilon. And I'm saying x sub 13 minus x is less than epsilon.
That's not true though.
It is. For this picture right here. Here's x sub 11. Its distance from...
Wait, you're saying 11 lies with, x of 11 lies within...
Here's x sub 11. I just counted out the points from this picture. Just from a concrete picture.
Okay. Oh, so what you're saying is x of 11 lies within the...
The distance from x of 11 to x is less than epsilon.
So everything higher, everything greater than 11? Holy...
You're getting it. Perfect. So I was saying, look, x sub 11 minus x, that thing's distance is less than epsilon.
So what is...
And that's also true if you replace it with 12. And that's also true if you replace it with 13. And that's also true if you replace it with 1000.
So wouldn't x of 11 be on epsilon?
No, it's inside of it.
Okay, what's on epsilon?
Maybe there's nothing. But hold on, I didn't have to use 11. I could have also just said, here's x sub 13. All that matters is I can find some point
That everything
such that from that point onwards, the whole sequence is in there.
from epsilon to x minus epsilon to x.
Yeah, so x sub 13 is within epsilon of x. So is x sub 14. So is x sub 15. So I could have also chosen my big N here to be 13. I didn't need to find the first one. I just need to find one. Such that from that point onwards, our whole sequence is within epsilon of x. So that x of n minus 14 is minus x. That distance is always less than epsilon for all little n greater than or equal to big N. So let me read this one more time, and I think you're ready to absorb it now. We say that the limit as n approaches infinity of x of n is equal to x.
Yes.
If and only if. For every positive real number epsilon you choose.
Real.
Pick any distance epsilon you want. For every distance epsilon.
Okay.
There exists a point in our sequence. A big N in our sequence.
Okay.
Such that the distance between that term in our sequence and x is less than epsilon for all little n greater than or equal to big N. So big N might have been 14. We're saying this is true if I replace that little n with any number greater than or equal to 14. In the case where big N, 13.
So that big N is...
So once you
that
choose
big-
it, go ahead.
So that big N is that little N, right? Your first little N.
It's not necessarily the first little n that makes this true. But we're saying as long as you pick little n greater than or equal to big N, then this will always be true now.
Oh, yeah, okay.
Okay, now you didn't have to choose, so we pretended over here you chose epsilon to be 1/2.
Mm-hmm.
Maybe you say, okay, you figured it out for 1/2 and you found from 13 onwards. What if I was more tricky and I picked a smaller number for epsilon? So rather than 1/2, I picked 1/10,000.
Okay.
So now we restart, and you pick 1/10,000, and I can hardly draw that. Here's x. X plus 1/10,000 is barely over that way. and x minus 1/10,000th is barely over that one.
Okay.
So now we zoom in on this part of the sequence. So zooming in, here's x plus epsilon, here's x minus epsilon. Zooming in on that right here, right? And now there's still going to be some points inside of here. Getting closer and closer to x.
Yes.
And now, maybe this point right here was x of 106. Then I say, look, from 106 onwards, my sequence is within that distance of x.
Doesn't matter if it's,
I didn't have to find the first one.
yeah.
I just need to find some point such that from that point onwards, my sequence is within that distance of x. You can pick any small distance you want, as long as I can show that if you go far enough in the sequence, we're always that close to x, then my sequence converges to x.
Okay, yeah, I see what you're saying.
So now,
let me repeat it to you, so if I get it. Okay, so, the limit to
the limit as n approaches
as
infinity.
n approaches infinity is
Of x sub n.
of x of n is equal to x if and only if for every, how did I forget that word?
The name of that symbol is epsilon.
Epsilon. For every epsilon with positive real number for n, right?
For every positive real number epsilon,
For every positive real number epsilon, there exists a number, a positive real number, right?
positive integer, because it's going to be 1 or 2 or 3 or 4 or 5.
Okay, a positive
Integer. Big N.
big N, that,
After you read existential, you always say such that for this part. So,
oh,
there exists a big N
a big N,
such that.
integer such that x little n is less than epsilon for every, right?
Away from x. X of
Away
little
from
n
x.
is less than epsilon away from x.
Away from x, for every little n, it has to be greater than or equal than n.
The big N that we found.
Big
over
N that you found for epsilon, right?
Perfect.
Okay, or your big N, yeah, okay, understand it.
So now, let's work with one of the concrete sequences that we already knew. So I already told you that the limit as n approaches infinity of 1 over n is equal to 0. Let's assume that we know that. Our intuition tells us that, right?
Okay, yeah.
So our intuition tells us that. So let's see. That means that this should satisfy that definition. That means that for any epsilon I give you, you should be able to find a big N such that this whole sequence is within epsilon of 0 from that index onwards. So let's try and play the game here.
You're saying x is 0?
In this case, x is
The
0.
limit is 0.
Let's pick one where x isn't 0. Because I think a 0 in there might confuse
I
you.
think I understand you. What you're saying is just x is 0, right? Or the limit is 0.
Okay.
1, okay.
Yeah, this time let's use 1, just so our zeros don't make things disappear. Okay, so what am I saying now? What I'm saying is now, if this is true, if the limit of this is equal to 1, so this is just going to be writing out some terms of this. Let me write the 1,000 term of this. The 1,000 term of that is 1,001 over 1,000, right?
Yes.
So we're getting really close to 1.
Yes.
Okay. So, then according to this definition, for any epsilon I choose, you should be able to find an index such that my sequence is within epsilon of x, or 1, from that point onwards. So here's the number I'm going to choose. I'm going to pick a small epsilon. What should we choose?
Let's go 10,000.
1 10,000.
Wouldn't it be 10,000 or not?
So here's our epsilon, 0.0001.
Oh,
Now,
okay.
if we're right, we better be able to find some point in the sequence such that its distance is less than 1/1000th away from 1 from that index onwards. So now our job is to find the big N. You with me?
Yes, yeah.
So I'm looking for the big N that makes n plus 1 over n minus 1, its absolute value, less than epsilon.
Yes. Okay.
I'm trying to make x of n minus x less than epsilon. Trying to find the big N that makes this true. Any big N that makes it true.
Doesn't have to be the first.
We don't need to find the first. You don't need to be super clever about it. We just need to show that there is some index such that that's true from that point onwards.
Is this how you prove that d limit is 1?
Yeah, I'll show you some, next time I'll do some basic proofs of what the limit is
Okay.
to show you how we actually prove it.
To find a big N.
So we're trying to find a big N, so that this is true for all little n greater than or equal to big N, right?
Yeah. Okay, let's go 100,000.
Well, first off, we can see that this number is always bigger than 1.
Right.
Yeah, obviously.
Subtracting 1 from it will be a positive number, so the absolute value here isn't changing anything. The absolute value of that is just that, right? In this special case. So now add 1 to both sides, so I need n plus 1 over n to be less than 1.0001.
I have a question.
Go ahead.
If no matter what number you plug in there, you'll always get 0.1, right? Well,
Let me just plug one in really quick. Plug in 2. You get 3 halves,
no, okay, not
which
every
is
number.
1.5. When you plug in multiples of 100, it ends up, or multiples of 10, it ends in 0.1.
Yeah. So even if you do 100,000, you can't pick that number. You'd have to pick 333,000.
100,000 works in this case.
100,000?
Uh-huh.
No, because it'd be 100,001 over 100,000. That's 1, and all you're left with is 0.1.
So if we plug in 100,000 for n, what do we get?
You get 100,001 over 100,000.
Right, so you get 1 point, the tens, the hundreds, the thousands, the 10,000s, the 100,000s. So if I plug in 100,000, so this is what I get if I plug in 100,000, which is definitely smaller than that. Right?
Okay, yeah.
So this is smaller than that. So you already found a number. You said big N equal to 100,000.
I was thinking that the 100,000 cancels out and you're left with 0.1.
Right. You didn't have to choose 100,000 though. You could have just as easily said 100,000 and 2. And it would have been a slightly smaller number, but harder to quickly write out in our heads.
I thought you just got left with that 0.1, 0.2.
So notice now, if we plug in 100,000 into this, it's less than this number.
Oh, that's what the big N is.
Yes.
That's your...
Plug in that number for big N, and it's less than this, right?
Yes.
And if this is less than this, then this minus 1 is less than this. Anytime this is true, this is true.
Yeah.
Because they say the same thing. This is just shifting the 1 over there.
Yeah, it's just taking away that 1.
So if big N makes this true, big N makes this true.
Yeah.
Yeah. And now, what if I pick a number bigger than big N? Is it still true?
Yes.
Yeah. Any number bigger than big N still makes it true. Because as I plug in bigger numbers for N, this whole number gets smaller. It gets closer and closer to 1. It keeps getting smaller and smaller, closer and closer to 1.
Yeah.
So this gets smaller and smaller for bigger and bigger numbers I plug in. So when I plug in 100,000, it's already less than this. So if I plug in a number bigger than 100,000, it's going to be even more less than that. So you found some number big N, such that from that point onwards, this will always be true. This will be true for all little n greater than or equal to the big N you found. You found them, 100,000.
Oh, yeah. Okay.
You could have found another one, 200,000. And if I would have picked a smaller epsilon, you could have just found a different big N. It doesn't matter what epsilon I choose, you can always find a big N that makes this work. Right. That's what it means to say that a sequence converges to a number. So, or, sorry, I keep saying converges. It's the same thing. The limit as n approaches infinity of x of n is equal to x. What does that mean? It means that for any positive distance you choose, no matter how small, I can always find some index in my sequence, such that my sequence is less than that distance away from x from that index onwards.
Yeah. I understand what you're saying.
That's it. That is the full-blown definition of a limit. That's the big bad idea of calculus, the one that gives students so much grief. It's a pain to absorb that definition. There's a lot going on there.
Maybe you should just teach calculus. But
I do try and teach calculus. Never have students.
learn it.
Yeah.
Okay, I understand.
You're learning one of the big bad ideas of calculus. It is not easy to absorb this. Your book doesn't go into near this much detail.
Well,
They just give you the, yeah, you see what's happening. It is so zero, and that's what we mean.
Well, yeah. Well, if you were to throw that in front of me, and I'd read it left to right, but you have to read it left to right to right to left to left to right.
Yeah, you need to understand what it's all saying.
Right.
So, there it is. Next time, we'll go over that definition again briefly, and then I'll actually do a couple proofs of limits. I'll prove, like, this limit is in fact 1, show you how you do that proof. We'll prove some properties of limits, and then we'll be ready to talk about perimeter. Because where we're going with this, or sorry, not perimeter, circumference. Where we're going with this is, what's the circumference of a circle? We say first take the inscribed four-sided polygon.
Then you divide in half, divide in half, divide in half. Right.
So this is a polygon with 4 sides. Look at the perimeter of a polygon with 4 sides. Look at its perimeter. Okay, that's definitely less than the circumference, right?
Right.
For sure.
But now let's look at one with an 8-sided figure. If we instead of 4 sides did 8 sides, then that would look like this.
You can leave just the side.
And the 8-sided figure would look like this. And now we're getting closer to the circumference, but we still don't quite have it.
Oh.
So now you
And then if I would have used a
What-
16-sided,
now you have P infinity.
What would be your epsilon with this?
so what we're going to prove, now I happen to pick 4, 8, 16, whatever, but really what we're proving then, or what our definition of circumference is going to be,
It's gonna be limit.
is it is going to be the limit as n
P.
approaches infinity,
Or P, because we're talking about.
as n approaches infinity of these p sub n's. And by definition, that is going to be the circumference of a circle. It's the limit of what these perimeters go to.
The limit of n towards.
Yeah, as you pick bigger and bigger numbers for our perimeter, that's how many vertices we use in our regular polygon.
Bigger and bigger you get, the closer you
Right,
get.
I just happen to pick 4, 8, and 16 because that's easy for us to quickly draw.
Right.
But if we were to write this out for P100, P101, as we keep going further and further,
You can do-
P102,
Why can you do non?
But you would never
you just break it up into that many pieces.
that many points, right?
So I just divide each.
That many vertices.
Right, so now if we were to divide this up into a polygon with 100 vertices, so vertice there,
And
More than 100,
six.
but
and then make that regular polygon do, and calculate its perimeter, then we're getting much closer to the circumference of the circle.
But you
Right.
never get it.
But we never give it.
has infinite points, right?
Because it has there's an infinite number we can do. And so it's going to be the limit of the sequence is what our circumference is going to be, by definition.
Right.
So that's going to be the definition of circumference. It's defined in terms of a limit.
Okay.
So that's where we're going, and that's why we have to do all this groundwork.
Yeah, okay.
Okay. So that's that. Big lecture to swallow. Limits are hard. You do not come across a harder idea than limits in all of academia unless you go get some sort of like STEM field degree, like engineering or math or something like that. Outside of that, limits is one of the hardest concepts you have to come across. That's a very dense definition, hard to absorb.
Let's go through that one more time, please. Read it out. Read.
Read it out. The limit as n approaches infinity of x of n is equal to x, if and only if, for every positive real number epsilon, there exists a positive integer big N, such that the distance from x of n to x is less than epsilon for all little n greater than or equal to big N. That's reading it literally. Let me not read it so literally, but try and communicate the idea.
Right.
The limit's equal to that if and only if. For every distance, there exists an index in the sequence such that the distance from our sequence to x is less than our given distance from that index onwards.
So he's saying when you have epsilon, let's say epsilon's, think of any point, it could be 3.5.
Yeah,
And then you
absorb
can
it.
It means you can find a big N, any point beyond that